So welcome back again. We're going to start soon. I'm sorry. I haven't had time. Welcome back again. Our next speaker is Shreyasi Datta, and she's going to talk about bad is null via constant invariance.
Thank you very much. First of all, I want to thank the organizers for giving this opportunity. And I also want to thank Irina especially for organizing this online. Okay, so I will talk about a problem in Diophantine approximation and also show you why this problem is interesting and what are the tools that go into some of the proofs. So I'll start with a very classical result that is due to Dirichlet. So if you start with any vector x in Rn, you want to approximate birationals, and Dirichlet theorem kind of tells you how well you can approximate. So in particular, if you fix the error in terms of the rational that you are working with, then how close you can get to the rational. So it says that there are infinitely many p and q integers such that qx minus p, the norm, this is, you can take any norm, but here in particular I'm working with the sup norm, that should be less than 1 by q to the power 1 by n. And this happens for infinitely many integer vectors. Okay, so this is a classical result, and the main question that we want to understand is that what happens to this constant here if why is it 1, and what can we say more about it? So in particular, the question is, can you make this constant 1 go to 0? By which I mean, so let's look at the set of, let's say, C, where it's exactly the same statement as this. So let's say star holds. That means you have infinitely many P and Q, such that this inequality is replaced by 1 is replaced by C. And the question is, can you make C as small as you like? Okay. The answer is no. First of all, we can look at the golden ratio, and one can show that, in fact, there exists a particular constant 1 by square root 5 or some 1 by square root 5, such that you can actually show that you cannot go beyond that. In fact, which means that for all P and Q, you can get actually the reverse inequality to this, the one that you get from the Dirichlet. Okay, and we know that the continued fraction expansion of this golden ratio is 1, 1, 1. So maybe you can ask, in general, given any real number, can you say anything? If you know their continued fraction, can you say anything about that number? So actually, if you know that the AI, so the x is a naught, a1, these are the I don't know what are they called. Okay, so if these AIs are bounded, then you can say that the answer to this question is no, which means that you cannot do this you cannot improve this Dirichlet's theorem, the constant 1 by any small enough epsilon. At some point you have to stop and you will get the reverse inequality. Okay, so that means in this talk we want to understand these kind of objects for which the reverse inequality holds, and in particular we call them badly approximable numbers or vectors. So that means that there exists some constant. That constant may depend on the point that you started with. such that for all P and Q, you have exactly the reverse inequality to the Dirichlet's theorem. For here, the 1 is replaced by C. Okay, so this is the set that we are interested in. And the main problem that I want to talk about is that, okay, if you start with some Borel probability measure on R, what can you say about the size of this set? First of all, one can easily see that, well, if you have some number which is bad, you can take any integer multiple of that number and it will be also bad. So that in particular says trivially that this set is actually countable. So it has at least countably many numbers. Okay, so this is the question. So obviously it depends on what measure you start with. So first of all, if we start with mu to be the Lebesgue measure, so let's say lambda, then we know that this lambda, so this is the Lebesgue measure. Then we know that lambda of bad is 0. And there are a couple of ways to say it. So one is instead of working with bad, you work with something more general. I'll not talk about them, but they are coming from something called Hinton's theorem in Diophantine approximation. But basically, it's better results that gives you that this set has measure 0. Also, there is another way to look into this problem, which comes from homogeneous dynamics. So what you do is that, okay, so you start with, so I will explain this direction a bit. Okay, so let's say we start with a vector x in Rn. We can look at x inside a matrix. So let's say you take identity matrix here, the last column you replace by x. So x is a vector, and then 1 here, and otherwise, okay, so this is 0. So let's call this u of x. And you can kind of look at x as ux zn plus 1. This is a lattice in Rn plus 1. And in particular, this belongs to the space of unimodular lattices. This space. So, okay. So what we are going to do, let's go to this page. So you start with this point ux zn plus 1 in this space. And you act this point by a geodesic flow. So the GT, let's call it. So where it will be expanding in the first n many coordinates and then shrinking in the last coordinate. So if you look at this orbit, x it turns out to be, so this is due to Dani. So Dani's correspondence. The thing that we are interested in, that x is bad, has a correspondence, is that this orbit GT of this point ux is bounded. Okay. So we know in particular that this GT acts ergodically on SLN plus R mod SLN plus C. So in particular, we know that if you take the measure of the natural measure, or the Haar measure on this unimodular space, this orbit, the bounded orbits must be measure 0. So all this lambda in this in this space of unimodular lattices, such that this orbit is bounded. This has measure 0. And then you can actually reduce with some work, you can actually reduce this lambda by, replace lambda by u of x. So actually, there is a little work which tells you that, okay, so x such that GTUX and here I have lambda. Lambda is the Lebesgue measure, so this turns out to be also 0. So, and because of this correspondence, it implies that bad has Lebesgue measure 0. Okay, so a natural question is it all, I mean, for what kind of measures this is true? And if you have any example where it is not true, meaning, is there any, so I'll go back to the problem again. So do we know about some Borel probability measure where bad is not 0? In fact, there are many such measures that are supported on, they are called Kaufman measures. And they have some Fourier decay properties, and people's, yeah, so there are a class of measures for which this is, you don't expect this to be 0. So for this talk, I want to focus on something that for which you can actually show that mu of bad is 0. Okay, all right. So as you can see here, that this homogeneous dynamic statement depends on the fact that GT acts ergodically with respect to the Haar measure. Now, if you replace the Haar measure by some other measures, you may lose the invariance or you may lose the ergodicity altogether. So you cannot use this just this homogeneous dynamics directly. So you need to prove something more than that. Okay, so I will focus on this measure. So let's say I'll take F, a map, let's say from a d-dimensional Rd to, so let's say some open set in Rd to Rn. So you can always think of a curve from in R2. And we will be interested in this measure. So this is the measure that is supported on the curve f of x. And the question is, what can you say about f star lambda of bad? So why this problem is more interesting is because here you have dependency on the chord, like, so you have so f of x is so this is your f of x. So if you try to compute the f star of lambda, there is a dependency on the coordinates. That is why it becomes difficult to even compute volume of a ball under this measure, right? Okay, so previous results. And these were results by Beresnevich, Barnick, Kleinbock, Marglis from 2002, and also a result by Beresnevich, Dickinson, and Villani. And so this is also from 2004. And also there are some results by Nimisha, where they prove that in all of these results, they prove that if you have some condition on f, so in particular, if let's say f is analytic plus f is not flat, By not flat, I mean that if you look at the image of F, there is no point, there is no part of the manifold or the curve where it is contained inside any affine hyperplane. So in particular, affine subspaces are not included. And you should have curvedness in all part of the manifold. Then F star lambda of bat is 0. And they use, so this previous results uses prove some more stronger result that I previously mentioned, like Hinton type results, in order to show this. And they use tools from homogeneous dynamics. So what we prove, so this is a joint work with Beresnevich. Beresnevich, Ghosh, and Ward from 2023. So we proved that, okay, you just need to have the condition that F is C2. And then you have the result that F star lambda of pad is 0. And our method is completely different than any of the methods that were dealt with before. In particular, we don't prove anything stronger than this. We don't prove Khinchin type results. So we have much less restriction on the manifold. We have almost no restriction on the manifold. And in fact, this we have the results for more general other than bad, meaning, so I'll not get into that, but one can, so let's go back to the beginning. So here, you can see that in the definition of bad, I can just rewrite this from taking this 1 by n to this side. So I can write this. Okay, but there is no reason to put same weight on every coordinate, meaning I can replace this n by some weight. So summation of wi is n, and call this, let's say, w. And I can repeat all of these questions as before. And many of these methods will not work if I work with any general weight, because the coordinates are expanding in different rates. So you cannot apply, for instance, even applying this homogeneous dynamics method, like this thing, the little work may become very difficult. Okay, and we also have the result for F star lambda of that weighted set to be 0. Okay, so I want to probably say only a few words about the technique of the proof and why it's different. So essentially, so let's go back to the definition of bad. So the bad was that, okay, you take everything that you get from Dirichlet, which says you get everything, Rn, minus the points for which you can do as good as C by. So basically, you have that Qx minus P is less than C by Q to the power 1 by n for infinitely many Q. And then you have this. So bad is where you cannot do that. So that means there exists some constant that the reverse inequality holds. Note that this is nothing but, this set is nothing but a lim subset of balls, union of balls. So I can write this as P by Q and then C by this. Okay. And here we want to consider f star lambda of bad. So what we actually do is that we prove, so let's call this set as W of C. So our strategy is to show that f star lambda of WC is f star lambda of WC prime for all C and C prime greater than 0. So in particular, we know that W of 1 is everything, right? So we get that this act. So by showing this, so this is the main result of the paper, that we prove some constant invariance, that even if you change the constant from C to something else, you still get the same size, which implies that the f star lambda of this bad is of size 0. So in particular, we develop a method where you don't actually see f star lambda, but you work with any measure, any Borel probability measure mu, and you have some condition on mu such that we have the constant invariance, and then we show that f star lambda in particular also has that constant invariance. So this is the difference from all the previous works, because in all the previous works, they actually try to prove uh, these kind of sets, but not by some not of this simpler looking function C by q to the power some power, but they actually wanted to prove something like let's say sorry, this is one. So the previous results, they had a lot of restriction because they were proving something stronger, which was implying that bad is null. But here we have exactly the our method is only aiming to prove that f star lambda of some measure of bad is 0. Okay, I want to, I think, stop here. I guess my time is up. Thank you very much.
Questions? Okay, I guess I'll improvise a question. So you say you need a C2 function, but can you go lower?
No. There is some Taylor expansion that we need to use, and we need at least C2.
Can there be counterexamples if it's lower?
But
do you expect that it could be false if it's lower? I mean, could there be counterexamples?
That's a very good question. Yeah, I don't know. With f star lambda, I still expect it to be true for like for smooth measures like f star lambda. But there is no such example of C1 maps.
Can you see me now? Okay.
Yeah, yes.
And do you have more details about the support of the function? Like the support of the measure you're looking at?
Yeah, so this is a map. So, okay, so F is a map from some Rd to Rn, right? So you can basically take any C2 manifold. The support of the measure f star lambda is nothing but the image of F, right? So f star lambda is f star lambda of A is the definition is it's the push forward measure. So it's lambda of F inverse of A. So the support of this the support of this measure is the image of F, which is a manifold. So you can actually work with any manifold because you can look into only the images of open sets inside the manifold. That is enough to prove. So in what I'm saying, yeah, actually we are proving that if you take any C2 manifold, then the barely approximable points inside the manifold is of size 0.
Yeah. So thank you very much, and let's thank the speaker.
Thank you very much for joining.
Yeah, and so we have a 30 minutes break, and our next speaker is Shabnam Akhtari, and she's coming from Penn State University, and she's going to talk about a quantitative primitive element theorem.
Hi, okay. Thank you so much. I would like to start by thanking all of the organizers, scientific committee, and of course, all of you who are here. Like many of you, I'm enjoying my stay in this beautiful city very much, but also the conference by itself has been really amazing. It's so refreshing because it's a long time for me since I have been in a conference that I meet many new people because you start doing research and after a while you just go to conferences exactly in your area. And then it feels very nice to meet new people, learn some new ideas and be like going back home and just have more motivation. Also, I want to give a shout out to all of the people who are engaged in organizing this event. I appreciate everything you have done, but I particularly want to point out that it's really great how you thought of including all gender minorities. It's very easy and quite common, unfortunately, to just have women conferences and ignore the fact that there are other gender minorities. So it has been really great, and I hope that it has worked out for many people who were interested in coming. So thank you so much for everything. And here's my talk. I'm a number theorist, and one of the reasons I love number theory, and I started doing that because I couldn't choose what to do. I loved all sort of mathematics, so I wanted to do everything. And I'm not claiming that my research is actually using all the techniques, but I enjoy all sorts of math. And maybe today, I don't know how far I get and how much I can talk about the dynamical methods that has been used in this work. But the least thing I hope to do is to give you some general ideas of the objects I'm thinking about and maybe point out that, oh, we use some dynamical things here, but maybe I don't get to explain the ideas that you might be interested very well, but I hope that I can at least clarify some definitions. So you'll see I have lots of definition. It might be repetitive for many of you, but please, if you have questions about the basic stuff, ask, because that's the least thing I hope to cover here. So I am going to talk about primitive element in a number field. So let me just start with definition of a number field. An algebraic number field is simply a field that is finite extension of the field of rationals. That's all you need to know about the definition. But then soon you will see that they have lots of good properties, and they have been known forever. Like this is a very, all the results that I'm covering in the beginning are very classical. So basically, with what I said, you can imagine a number field as a subset of complex numbers. We can embed them in the complex number, and that's the field of rational numbers, and I attach a finite number of algebraic numbers in it and make a field. That's all. And of course, because the number field is a extension of Q, I can also think of it as a Q vector space. So it's going to have a finite dimension, and I can look in computationally. It's not easy, but I can look in theoretically and find some generating elements that give me the vector space with a certain dimension. That dimension would be the degree of number field as well. And the rest of things probably you are very familiar. You have worked with polynomials, and that's just the basic definition of what an algebraic number is. It's a number that satisfies a polynomial with integer coefficients or rational coefficients, doesn't matter. But if you manage to write a polynomial that all of the coefficients are integer, but the leading coefficient, the first one, is 1, any root of that would be an algebraic integer. So algebraic integers are a subset of algebraic numbers, and I will give you more example. And but what is the primitive element theorem? That is my my main focus here. The primitive element theorem, if you have taken any number theory course beyond the elementary one, when you learn how to calculate GCD or everything, after that, one of the first thing you learn is that if you have a number field, you can always find one single element that gives you everything in that over Q. And that's quite impressive. Maybe when you learn it, if you saw that theorem, it doesn't look that much of a big deal, but once you start working with number fields, you just see that having one single element that by itself generates everything over Q. Basically, you can take elements from Q, rational numbers, and multiply them to alpha or powers of alpha and get everything in your number field. That's quite impressive, but again, this is a very ancient theorem, and it comes from generally a theorem in algebra that I wrote in the middle of this page, but it applies to number field, and it's just as algebraic objects are separable, so it's not, it's a very immediate thing that they are algebraic number fields are also primitive. They have a primitive element. But here is the question that I want to ask today, and that's what I mean by quantitative. If you have a number field, you have a generating element. Right away, even if you don't think very deeply about this, you can see that if I have one generating element, I have infinitely many. You take the alpha that I gave you and add any integer or rational to it. That would generate the field too. And there are many other ways to have generating elements. So there are infinitely many. So the main question of today's talk is that which one is the smallest? How small can be the generating element? Meaning that look at your field. It has infinitely many elements, first of all, but it has still infinitely many special elements, which are elements that generate all the field. But among those, of course, you can make them bigger and bigger in size. But among those, is there anything that that is smallest, and you can't make anything smaller than that? And the thing is that such elements should exist, and that is known by, I just mentioned the property, something that is called Northcott property. So once you stay in a number field, algebraic numbers, either an algebraic number is 0, or it can be too close to 0. And again, for those of you who know a little bit about Diophantine approximation, or you learned something about it in earlier talks, you know that a number field has only algebraic elements. And an algebraic number cannot be too close. If it's not rational, it can be too close to a rational. So you have all the rationals in your number field, but also a bunch of algebraic elements. So they keep a distance from rational once they are not rational. If they get too close, if a number gets very close to rationals, then that number got to be transcendental. So anyways, in principle, we have known that there is a small primitive, or the smallest primitive element in our field, but the question is that how small? Or like, if you give me a field, what do I know? What do I need to know about my field to make sure that, and to make sure that I know something about the size of the smallest primitive element? So just some examples. This is for those people who see the definitions for the first time. None of the examples are deep, but for example, what Primitive element theorem says, like, look at the field Q join a square root of 2 and a square root of 3. This is a field, finite field over Q, and the primitive element theorem says that you can find a number in the field that generates everything by itself. And in this field, it happens to be just addition of these two elements, but it's not always that easy. And another thing that I want to mention on this slide is that the nice thing about primitive element is that it gives bases that are all powers of that element for K as a vector space, because that element is an algebraic number. It satisfies a polynomial. So therefore, once you get to the degree of that polynomial, all other bigger powers of alpha are covered by 1 alpha alpha d minus 1. So, and then that's a very nice property too. And soon you'll see how interesting it is in defining different absolute values on your number field. The fact that you have primitive elements and the powers of that take care of your all the elements. So basically what I'm saying here, all the elements of K can be written as a linear combination of these elements in the set 1 alpha alpha squared to alpha d minus 1. Here is, I'm repeating, I said already what I'm thinking about. So the main problem is there a smallest element? Yes, there is. How small it is? And then is there any way, any constructive way to find that element? Here is a question that is very simple, basic question. It's basically the same question that I said, but like we are telling what we want, and probably you don't know many of the things I'm talking about here. So Rupert in '98 asked, is there in every number field K, is there any element that is small in a certain sense? Height of alpha is less than or equal to a constant that only depends on the degree of the number field, but not the specific elements, times the absolute value of the discriminant of that to the certain power 1 over 2 times d. D here and along the talk is going to be the degree of your number field. If you are thinking of it as a vector space, is the dimension. If you are thinking of it as an algebraic extension by alpha, d would be the degree of alpha, the degree of the minimal polynomial of alpha. But then I have to tell you what are these h and delta. So a delta of k, as I said, is the discriminant of the field. And I will talk about the discriminant a little bit more. I will never give you today a definition for that, but I will give you some ideas that what it does. And then h is going to be a multiplicative function. That's the height function. It has property of a height function. In our work, we are using the way height, which I introduce later, but generally you want to have a way to measure like the size of your elements in the number field. And there are many different heights that you can use. Way height is very helpful here, especially when you want to talk about the discriminant because they are related. And the main result that I am focusing on is a joint work with Jeff Waller and Martin Widmer, and the result that hopefully I get to show you at the end is relatively recent progress. We are going to answer this question of Rupert mostly, and the answer is actually yes, that you can find a small enough generator in every number field, but there are exceptions, and we also identify what could be an exception. And I wrote a small, we identify a class of number fields which might not have a small integral generator. Those are the number fields that may have a small generator, but our method actually ends up only finding generators that are also algebraic integers. So the point here is that if you work harder, maybe you can find smaller elements that are generating, but they are not integral. And we don't know that. And that part is actually, I believe that's the part that we are desperately in need of dynamical ideas, because we find a small integral elements that have heights that are small, but not as small that we want. So we are hoping to divide them or basically multiply them by some integers and make them make them have height. So we are hoping to get our integral element that has the smallest height that we could find, but divided by some integers and still have a generating function, but make sure that that generating function has a small height. And that's the thing that makes us go through these loops of things that are equivalent in our number field in terms of generating property. They give us the same elements, but we want to control their height, and that's the part that is remaining, and we haven't been able to do that. Okay, so I'm looking for a small element, so I got to tell you what the size of an element is. And I started by telling you that, well, you can think of any algebraic number field as a subset of C. So the most reasonable height is that, oh, isn't it in C? So just put the absolute value on it. And surely we can, the regular Hermitian absolute value, surely we can. But the thing is that if I have a number field, really the definition of number field is this quotient field in the bottom of this page. You take all polynomials with coefficients in Q and multiply by the ideal generated by the minimal polynomial of a generating element. But this is the number field. This is abstractly the number field we are working with. But if I try to think of it as a subset of C, I have different ways to think of it. I can think of any root of this irreducible M of X, alpha 1, alpha 2, alpha D, and take any of these roots and join it to Q. That's a number field inside C. But all of these roots, in their own right, they can give me a number field. I might have repeats, I might not. So when I imagine an algebraic object, this quotient field, in C, I have the different ways. Not necessarily distinct, but sometimes they're actually distinct. So which one I realize as my number field? All of them are isomorphic. Algebraically, they are the same. But in terms of when you want to do geometry or when you want to think about size, they're not the same. If alpha 1 and alpha 2 are the root of the same polynomial, once you get the regular absolute value, they can be very different. So really the question is here is the distribution of the size of different roots of a polynomial, which is a very difficult problem by itself. But if you limit yourself to polynomials that have only integer values, is much, much harder. So if you do number theory or you know some number theory, what we are asking is that the question of how the different roots of a given irreducible polynomial, integral polynomial, are distributed. And I mean, it's hard to talk about that and answer it completely, but the whole idea of valuations and different absolute values in number fields is around this idea. So I'm just reminding you, if I have an algebraic number that is alpha, I can write a minimal polynomial for this. That's the smallest degree polynomial that alpha satisfies as a root. We can define the naive height of alpha, and that's a very helpful height. It's very reasonable to think of the coefficient of this minimal polynomial as identifying element of your algebraic number, and you just take the biggest absolute value of the coefficients. That's called the naive height. It's truly a simple height. It's acceptable. It works very well. And the other height that is very height, and I'm going to use, it's more appropriate for our purpose in the sense that it talks about all the roots of minimal polynomial, and certainly it considers all the embeddings, all the ways that I can embed my number field in in complex numbers. But the nice thing is that the naive height and the absolute Weil height are actually related by inequality. So they are equivalent in the sense that you can write inequality that compares each of them with the other one from both sides, and you have constants in your inequality. So, but I want to work with the absolute Weil height, and I really hope by now I convinced you why I need to consider all of the roots of my polynomial, not just alpha 1. Just because their size are different, and if we realize different number fields, but they are isomorphic, we want to come up with the same size for either our alpha or even the height of our number field. Okay, so the Weil height, the definition, I don't need you to memorize that definition, but I want you to have an idea as I speak further. You take the leading coefficient, that is an integer, so I made sure that my minimal polynomial, all the denominator are cleared. So I take the leading coefficient a sub n, absolute value of that, and then I multiply all of the roots, but I just want to consider the roots that are in absolute value greater than 1. That might look unnatural if you know that you do not know the theory here, but actually we have this beautiful formula. It's the product formula, and the contribution of, like, when you multiply all the roots together, and I mean, actually, it's not very hard to see for the polynomials, because when you multiply all the roots together, you know, you get the A naught. If you think of your polynomial as x1 minus alpha, x minus alpha 1, x minus alpha 2, and so on, once you multiply them all, you get an integer that is exactly A naught divided by AN. So here in the Weil height, by including only big absolute values bigger than 1, I actually consider the rest which are inside my AN, because all of them multiplied together give me A naught divided by AN. So they are all playing a role here. And in case you know more about this theory, of course, this absolute value of AN is the contribution of your p-adic valuations or non-Archimedean ones. But I'm not going to go further in that direction. They play a very important role in our work, but today I want to keep it very basic. So as I said, the absolute Weil height is defined like this. And even though I'm not going to use Mahler measure, but I feel some of you might be more familiar with Mahler measure. Mahler measure is basically the nth power of the Weil height. And if you don't know this formula that I wrote below in on this page for Mahler measure, you might have seen it as an integral, which is, to me, an absolutely fascinating fact that the Mahler measure is the geometric mean of a function. It's an integral. It's a very continuous thing to calculate, but you can write it so discretely as I wrote it here. So this relationship between the Mahler measure of polynomials that have integral coefficients is quite fascinating and helpful in the theory of height functions. But I'm not using that. I just wanted to tell you in case you are more thinking about Mahler measure. One nice property of Weil height that I work with now, and we choose it for that reason over Mahler measure, is that if I think of an algebraic number alpha, that algebraic number can be in many different fields. Like, so for example, if you think of a square root of 2, it's in the field Q join the square root of 2, but it's also in a field like Q join a square root of 2 join a square root of 5. So you can go forever and fit it in the fields. The height that we work with, which is the Weil height, it does not depend on which field you are working it. The height of absolute value of a square root of 2 always would be what it is, 2 or around 2. And that's the job of 1 over n. That's the job of the degree, that I kill the relation between alpha and what number field it is in. So I defined algebraic integers in K for you, and as I said, these are those algebraic numbers that their minimal polynomial over Z has leading coefficient 1, and they have nice property. For example, they form a ring in your field, and we call that ring O sub K. And what I want from them, I want them to be like integers in Q. Like when you have rational numbers, the set of integer are a ring. And also what you can do, you can take any two integer and put the non-zero one in the denominator and make all of your Q. So that's the role of OK, the set of algebraic integers in your number field. So as I said, Z, the ring of integers, is the ring of integers of Q, but you end up having these kind of rings in any number field. For example, if you work with the roots of unity, you have a cyclotomic number field, and it's very easy to calculate. So the number field would be Q joint. Here I chose a prime number for technical reasons to have a nice example. But if you join, I think I wrote C here, but I meant to. So anyways, C sub P is a root of unity. Join it to Q, you get a cyclotomic field. But then if you join it to Z, you get exactly all the integer elements in your field. But it's not that easy to calculate this for, like, you can't just get any generating element and join it to Z and get your ring of integers. Sometimes it's just more complicated. But the thing is that the set of all of those numbers give you a ring. And that's another very interesting question, how to find a ring of integers based on one element in your number, and whether there is such thing. That's a different area I'm very interested in. But let me just focus on what I'm talking about today. But all I need today is that such ring exists in every number field. And another fact that you learn early on in algebraic number theory is that every number field has an integral basis. Remember, I told you I want something like Z for Q. But now this is the thing that gives me the 1. You can add 1 to itself, and you can get any integer coefficient of 1 and get all the integers. But if you multiply 1 to a rational, you get a rational number. So in number fields, we do have this generalized. You have an integral basis, and the number of integral bases is exactly the dimension of your number field as a vector space over Q. But this is the beautiful, simple, but really helpful property of integral basis. You can find these elements, omega 1 to omega d. They generate your number field over Q, and they exactly generate your OK over Z. And here is when you can do Diophantine approximation. Why? Because if I am looking at for elements that are algebraic, every element is algebraic. Looking for elements that are integral, that are algebraic integer, I write x1 times w1 plus x2 times x1 omega 1 plus x2 omega 2, and so on. And if I'm searching for integers, I'm only allowing myself to find x1, x2, xt that are integers. If only one of them is not integer, I'm out of the ring. I'm still in the field, but I'm out of the ring. So there's this nice correspondence between, like, this omega 1 to omega d, like basically map Z to the D to my ring, and Q to the D to my whole field. And you can, if you, I don't know if anybody is interested in that kind of stuff here, but if you look at norm form equations, you are looking for all the elements that have a specific norm. The existence of integral basis is very important, because you can talk about your elements as a linear combination of this, and then limit your search to Z or Q. So And what I'm trying to say is that O sub k is actually a lattice. It forms a Z lattice in RD, and that is the fact that helps us do some geometry of numbers. Remember, I'm going to talk, or I'm aiming to find the size of different things and see how small they can be. So it's pretty cool to be able to work in a lattice. And what we see in algebraic numbers and also algebraic integers is that if you look for algebraic integers, they're completely discrete inside. So if you move from one to another one, your size has to change meaningfully, and that helps our search process. And I must say that none of the stuff that I said so far is particularly new. We have known this forever, but then the use of them in our work are quite helpful. I promise that I will talk a little bit about the discriminant. The discriminant of a number field is an invariant that measures the size of basically the ring of integers. So discriminant by itself can be thought of as height. And I wrote 3 sentences here. The last one is about ramification of primes in your ring of integers. I don't even want to talk about this, but my point is to say that discriminant has lots of good property. It has analytic property, it has geometric, it's the volume of a region. It's somehow the fundamental domain of your lattice, basically, a square of that. And if you want to do algebra, which we do in our work, but I won't talk about it, in your number field, it just tells you the behavior of primes and how they split in, like you have some primes on Q, and when you go up to your field K, how they split in the field and so on. So, which is not the focus of today's talk, but it's also by itself is a measure. And how you calculate it in a vague form, you basically find a basis for your number field as a vector space and look at the different embeddings of that and shape a matrix that is D by D, where D is your degree here. And you find the determinant of that matrix. That should be obvious. It's just because I'm thinking about the discriminant as a volume. But I wrote it's an invariant measure, and by invariant, I mean it doesn't matter which basis you find. You always get the same thing. So you always have a discriminant attached to your number field that has the same value, doesn't change with change of other bases or whatever you use. It's actually going to be wonderful in many problems, especially in arithmetic statistics. We are very interested in ordering number fields by their discriminant. But it's a quite hard problem because the discriminant really talks about all the things in your number field, but in such a concise way. And that would be wonderful if we could decide based on the discriminant only all the properties, and we think it should be possible, but it's very hard to prove things. So, and again, I remind you what's the question that we are thinking about, and it's the question that whether there exists an element that is small enough, and that's why we have the discriminant in this question, because it's a very wonderful invariant attached to your number field, so you want to compare everything with that. And again, obviously, I don't expect you to memorize this formula, but what Rupert wanted was that the height of the a small generating element is controlled by the discriminant of the field in absolute value 1 over 2 times the degree. The question was answered by Rupert for quadratic number field right away when he thought about this, and the answer is yes. We can find a small element that is smaller than the discriminant in quadratic number field, and if the quadratic number field was real, then he could find an alpha that is actually an algebraic integer, not just an algebraic number. And I have written an example feel free not to look at it. But if you are number theorists and this kind of things excite you, enjoy. But if not, the whole point is that when we are in quadratic fields, it's very easy to calculate the discriminant in quadratic number fields by just knowing what generates your number field, and your number field is generated by a square root of an integer, basically. And if you wanted me to simplify that, it's like when we have a quadratic polynomial and we have this b squared minus 4ac, that gives me how the roots are distributed, where are the two roots. So therefore, computing discriminant is quite easy. And again, there are classical results that help you write the discriminant, but also the ring of integers. But here is the example. If I, in the quadratic case, if we only looked at algebraic integers and we were interested in finding a small element in the ring, we would never, ever find a small enough number as Rupert wanted in the question. I hope that if you are following this computation, you see that, but here is the point of this slide, that all the algebraic integers have quite big size. They are of size delta to 1/2, which is not 1/4. I want 1/4. So if you are only working for in imaginary number field, which means that this m below the square root is negative, you have no hope of finding an integer. But you do find a regular algebraic number that generates that. Rupert, initially, I mean, the paper is very nicely written and it's very easy to understand, and it looks simple, but one of the results that he used is a result of Duke, which is quite deep, and that's a result that gives asymptotic distribution over integral binary quadratic forms, and it's just to point Higner points on them. And when they are positive discriminant, then it has the aversion in geodesics with positive, like in the case of positive discriminant. But this work is quite deep, but and it's really influential. And it's amazing that such a very simple classical question needed this method to only be answered for quadratic case. But another point of this work is that it's really not easy to generalize it to higher degrees. So when you want to prove things for higher degrees, I mean, maybe someone could do that, but it's really difficult to extend this work of Duke to any other number field, and therefore we had to think of other results or other methods. Let me see. Okay. So I want to go back to the idea of how we are talking about the size of an element. I said that Q is generated by one element, alpha. That's a number field. I wrote the minimal polynomial of alpha. This minimal polynomial, of course, has some real roots, some complex roots. The number of real roots plus the number of pairs of complex roots. This is a real polynomial, so complex roots come in pairs. And this fact is quite interesting in the theory of valuations. So R plus 2s is going to be the degree of my minimal polynomial, therefore the degree of my number field. I call K totally real if there is no non-real roots, and I call it totally complex if there is no, all the roots are non-real. And here was the idea of embedding K into C. And I said before, if you have a number field, each of us can pick one, our favorite root of the minimal polynomial, and then make K look like Q joined alpha. So, but what we were doing actually, we were defining some embeddings. So these alpha i's are different roots of the minimal polynomial of alpha. So one of them is alpha, that gives me the identity. But generally, I get d different embeddings of a given number field k into C. One thing that is actually not very hard to check is that this, under the composition of functions, form a group. There is identity and so on. So this is called the group of embeddings of a number field, and sometimes we call it the Galois group of K over Q. It's a group, and one other than identity, one other obvious thing is the restriction of the complex conjugation on your number field that is obviously in this group, because it sends one root of the minimal polynomial to another root, and if there is no complex root, rho will be identity on your number field, but that exists. So, and maybe I should not define this, because at this point I'm pretty sure I'm not going to talk about valuations and places, but the whole point is that if you think of the images of alpha under each of these sigmas, you get different roots, but in terms of absolute values, the regular absolute values, you get the same absolute values if you have two elements that, like, if you have, let me write it, if you have rho and sigma, they send alpha to elements that they have the same absolute values. So it's just because it's the complex conjugate. So what matters here is that if you are going to define the concept of size that comes from measuring different values here, if you have any complex roots, you get only S contributions. Half of the complex roots give you the information you need. Here I'm defining a constant that is based on discriminant. It doesn't matter what the numbers are. What matters is that the dependence of the discriminant is exactly what we want in Rupert's question. So the discriminant showed up there with the same exponent that we want. And that is something, I summarize it here to show the result later on. But where do we get that? This is basically something that may look mysterious to you, and obviously I won't have time to explain it well, but basically this CK is the size of a unit ball in a certain ring that we define for our number field. If you are not familiar with rings of Adels in number field, don't worry about it, but just know that it's defined as an infinite product of bunch of local fields that come from Archimedean and non-Archimedean valuations. But what matters is that the Adel rings is going to be the quotient of that over our number field is compact. So we can start doing some topology and we can get close to points and see where the points are or whether they will be generating function or not. And also, like, another property of this field is that K, you can realize K as a discrete subgroup of that. And eventually we are interested in finding points in K that do something certain for us, generate the whole K. So it's going to be helpful to work in this setting. And you don't need to worry about it at all. It's quite technical. But what we are going to do, we are going to do some geometry of numbers here. But let me remind you, what is the classical or Minkowski geometry of numbers? So it's basically this simple fact. It's oversimplifying, but it's this simple fact that Z to the N is a subgroup of R to the N. R to the N is locally compact, and the quotient group will be compact. So, and then if you are interested, if you are given a region in Rn and you want to see if this has a root integer, if you want to see if it has an integer point, what you see is that you look at the volume of your region, and if it's big enough, it got to have a lattice point, a Z point in it. So that's the main idea of Minkowski. And of course, if the region was symmetric around 0, then you are sure that you get a non-zero integer once the volume is bigger. And that constant C that I told you is coming exactly from computing the the volume of a fundamental region, so that we make sure there is a point belonging to the number field in these Adel rings that is so big. And yes, so in our setup, what we are doing basically is adelic geometry of numbers, and then Minkowski's principle applies. There are technicality, but I'm hiding that here. And much before I get involved with this project, my two collaborators, Jeff Waller and Martin Widmer, worked on this in 2008, and they proved that if your number field K has at least one real embedding, meaning that one of these alpha to alpha d is real, then the answer to Rupert question is yes. And the CK that you see height is compared to that is the volume of that unit ball in adelic ring. But I want to, more than explaining anything else, I want to try to say why we need a real root. And the reason is simple. If you can work in a number field that is real, and you start looking at distances, and you find an element that is generating element, meaning that it has a full lattice associated to that, it's not in a smaller number field, then you get the size. And once the size guarantees to you the size of say the determinant is not 0 once you write the appropriate matrix or so on. So once you find that element, the size looks like, okay, it gives you a full lattice, so it got to be the generating element. But if you didn't have any real number here, all of your embeddings would be a complex number field. And you might be in a situation that you have an element that looks like it's a full lattice, it gives you everything, but you only know the size of it. And that beta that you found, it's possible that if your K is complex, what if that the size of these two elements, these two different things are the same? It might be in a real, let's write H here, in a real subset of that, and then it goes up and gives you the same size here. So we are worried, if we don't have any complex images here, we are worried that the elements that we find, and it has a small height because it's in the fundamental domain, is not generating, it's the generating of the real subfield. And that's where they stopped many years ago, but recently we revisited that. And the first thing that we observed is that, well, if your number field has a root of unity, you don't have to worry about that, even if you don't have any real embedding. You just do what you do there. You find an element. If it's generating, fine. If it's not, take the root of unity, multiply it to it. The root of unity, if it's not +1 and -1, is a complex thing, so it can't be in the real subfield. Also, a beautiful property of root of unity that by all these simple definition I gave you, you can do it quickly, but I tell you, a property is that the height of any root of unity is 1. So once you find an element with a small height, if you multiply it to any root of unity, you get the same height. And that's another property of height, that once you multiply two things, you can, of course, control that. So that was the first observation, which doesn't change the method that much. We have to just adjust something, but fine. But after that, I know I'm over time, probably a couple of minutes, but I just want to finish with 1 or 2 more slides. After this observation, we thought, okay, what could happen if K as a number field is totally complex, therefore we can't use the method, the result of Waller and Widmer from before, and it doesn't have root of unity in it. Can we find a small element? And then we studied what happens if K has no root of unity, and it's a very specific thing to ask from a number field, because between K and Q there could be many other number fields, and the root of unity, like it can happen in any of them. but we have to study what happens if there is no root of unity. And also all of the embeddings come down to exactly a real one. And that's the major work that happened there. And basically what we get is that if a number field doesn't have an integral generating that has the small size that we want, there's no root of unity in it. But also this group that I explained here is of very certain type. So I'm going to erase this and just talk about this group. It's going to be identity in it, of course. Let's write it, identity and row. But then everything else is going to be tau 1, let's say tau. I don't know what to write here, but let's write it tau L. And all of these are order 2. So it's a very specific Galois situation, Galois group situation we are. So we are only thinking about those number fields that have their embeddings generated by elements of order 2. So what happens is that either all of them would be rho, the complex conjugate, and we have a CM field. And the CM fields are quite fascinating, and the distribution of, and we are studying the distribution of their generating element, or all of these elements of order 2. And I don't know if you can imagine, it's very hard to find a number field that has no root of unity, because when you have all of these things of order 2, it cries for a root of unity, that it sends every element to its to flip it, like everything goes, every x goes to 1 over x or so, or it's fixed. So anyway, so studying this group and basically its behavior, which is very simple, if we don't have root of unity and no real embedding, leads us to studying the distribution of generally elements in CM fields, which, if you not want the definition, are fields that I always think about CM fields as generalization of quadratic number fields. Instead of being quadratic over Q, they are quadratic over a totally real field. And then here there are lots of cool things. I think I have lots of things to learn in this conference, even though CM fields are studied algebraically very much, but analytically there are lots of properties that we are exploring. And like one of the bottom of this slide is one of the things I want to emphasize on. A CM field is characterized by the following property. Every CM field has a generator, algebraic number, not integer, such that all of its images in C have absolute value 1. And that is a very specific thing. So anyways, that's our result. And we have examples of CM fields that do not have a small height. So in that sense, our result actually predicts very well when is the situation that you can't find a small height. Thank you.
I have a clarification question. So the cyclotomic field is coming as a corollary of your theorem?
I wouldn't cyclotomic field. I mean, you can see it as corollary, but it's much it's better known. Yeah. So it has been known for a long time. Yes, because cyclotomic fields are very very easy, not easy, but we know a lot of good properties. The fact that they are cyclotomic, basically they are generated by an element of height 1. So they are the best prime example here.
So you mentioned that there are some complex, totally complex with no root of unity for which you have not the proper bound. Do you know the explicit number, what it is?
I will answer this, but let me know if I did answer your question. So for any field, regardless of their property, we will find an element that instead of delta k to the power 1 over 2d has 1 over d. That's for sure, for any field. So we always have a small integral element. But we can make that exponent better if we do have a root of unity or at least one real embed. Is that what you were asking? Yeah. But the worst bound, which is delta to 1 over d, is obtained in exact same manner in terms of geometry of numbers, but because you might be in a real subfield, so you push your element up, but then you make the size a square, so then you lose that.
Our next speaker is Noé Aranov from Technion, and she's going to talk about covering Radii in positive characteristic.
Okay, hi everyone. So thank you very much for having me here in this beautiful city of Pisa, and I'm very glad to see that there are so many women who do dynamics worldwide. So now I'll get to my talk. So I'm going to discuss covering radii in positive characteristic. We'll break down all of these words for everyone who does not know this. So the first one is covering radii. So what we see as a covering radius is the following. If you have some function f from Rd to R, which is positive, non-negative, and it has some nice properties, and you have some unimodular lattice. That is a lattice of the form G times ZD, where G has determinant 1. Then you define the covering radius with respect to f of lambda to be the smallest R, such that if you increase R slightly, and you look at the set of V's such that f of V is less than or equal to R, and move that along all the lattice points, then you cover all of Rd. Now, this is how we would write it out in an equivalent form. You could look at it in this form here, which is the supremum of all v's over, for every v, you look at the smallest u, but it minimizes f of v minus u. So now let's see how this looks like after all these words. For example, let's take f to be the L2 norm, which means that the set of v's such that f of v is less than r is everything in the interior of this circle for r equals 1. And we have here drawn the standard lattice, that's Z2 in this case, and we ask by how much must we contract or expand the radius of the circle so that we cover all of R2. The answer here is that the contraction ratio is 1 over square root 2, and you can see here that if we were to decrease slightly the radii of these circles, then we would have some gaps between all of these circles. And if we would increase them, then we would have overlaps over here or here, for example. So this is going to be the covering radius. Now let's talk, this is something called a covering radius with respect to a convex body, because that circle is convex. So a different way to view this is that we let C be a convex body with non-empty interior, and we can define the covering radius with respect to C of a lattice lambda to be the smallest r, such that if we expand the circle by r, then we translate it by the lattice points, then we cover everything. Now, how does this have to do with the previous definition? It's that this is a covering radius with respect to the function, which is the norm induced by the convex body. In this case, if we have a convex body C, we define the norm that it induces by being the infimal R, such that V belongs to the set R times C, when C is going to be a symmetric convex body centered at the origin. So then the covering radius with respect to C is the covering radius with respect to this norm. Now, for example, if we take any norm, then the ball with respect to that norm of radius 0, 1 just induces this ball, this norm here. So now, sorry, this covering radius here. Now we can ask about what happens if we take covering radii not induced by convex bodies. But before that, we can also discuss some results that are well known in this case. One of the well-known results is by Rogers from 1959, which says that the infimal covering radius along unimodular lattices with respect to convex bodies is going to be of order d to the log 2 of log d. Now, this was improved recently by Ordentlich, Regev, and Weiss to have the exponent being 2 instead of this terrible thing. Now, this may be nice, but let's try to understand what happens for a specific lattice. So if you take the covering radius with respect to the L2 norm of ZD, the standard lattice, then you're going to get square root d over 2, which fits our previous example with d equals 2. So now we can ask what happens if we take other covering radii that are not induced by convex bodies. So one particular example I would like to focus on is Minkowski's function, which is the covering radius with respect to this multiplicative function given by the product of the coordinates. So I just wrote out the full definition here if you prefer the geometric one, which is simply you take the set of V's such that the product of the coordinates is less than R, and then you just and you ask how large must R be, so that if you translate this along all lattice points, you cover the entire space. And now let's see how this looks like. So this set here is a star shape here. And you ask, by how much must we expand or contract this star so that we can cover everything? So now let's talk about the connection to dynamics, which is why I'm even here. And that is, firstly, this function mu, it's invariant under the group of diagonal matrices with determinant 1. So now we notice that since the diagonal group acts ergodically on the space of lattices, then we know that mu is constant almost everywhere. And we can ask, what's this almost everywhere value? So my advisor, Uri Shapirai, proved in his PhD, and this actually went into the annals because it's an amazing paper, that the generic value of mu is 0 for all. So, and now we also have a question about what is the upper bound. Obviously, 0 would be the lower bound as well. And there's another question about what's the upper bound of this. So in order to try to think about this, we connect this to dynamics as well, or in general to understand the set of values that mu obtains. So we can connect to dynamics in the following sense. If we have some set y, which is going to intersect every single diagonal orbit, then we know that the set of values that mu obtains on all the lattices is going to be the same as the set of values that mu obtains on y. And this way we can look at a smaller set and just focus on it. So this is the connection to dynamics. Now, I'll explain a short connection to Diophantine approximations, and this comes from Littlewood's conjecture. A lot of you may know of Littlewood's conjecture that says that for any two numbers, the infimum when you take all n's that are in n, let's say greater than 0, not 0, then the infimum of this n times the distance of n theta from 0 from the m from z times the distance of n phi from z is going to be 0. And this is something which obviously is true for numbers that are not going to be badly approximable. And also you can show well-known theorem is that it's true for all numbers besides the Hausdorff dimension 0 set. And this is a seminal result by Einsiedler, Lindenstrauss, and Katok. And now we can see that Minkowski's conjecture, what we have, the Minkowski function, is going to be an inhomogeneous version of it. So in this sense, we take this lattice here, which is given in this sense. And now we notice that if we compute mu of this lattice, then we get exactly this thing here, which looks a lot like an inhomogeneous version of this. That means you simply add shifts to every single coordinate. And now let's discuss some more things, which is Minkowski's conjecture. This is going to be about the upper bound. So the conjecture is for every unimodular lattice, we have that firstly, mu of the lattice is at most 2 to the minus d. Moreover, this bound is obtained. This is not hard to show that this bound is exactly going to be mu of zd. And moreover, it's believed that this bound is unique to the A orbit of zd. Now, this conjecture was proved for d which is less than or equal to 10, and this was proved over many years. There's proof going back to the early 1900s, and I think that there was a proof for d equals 10 from 2002 even, 2022, sorry. Now, one thing that I did in my thesis was ask what happens to all of this story that I just told you if we replace R with function fields. That is, we take a finite field FQ and we look at the set of all of these formal Laurent series. We're going to call this K tilde. And now we have to talk about what are all of our players in this setting. So I'll go over this relatively fast. So instead of integers, we're going to take these polynomials. That is, instead of having all of these guys here, you have only n, which is at most, which is going to be at least 0 here. And the field is, of course, K tilde. We need an absolute value. The absolute value that we define on any Laurent series is going to be q to the power of its degree. And instead of the L2 norm, we deal with the infinity norm. That is, if you have a vector, then the norm of that vector is going to be the absolute value of the largest degree, of the largest coordinate there. And the standard lattice, instead of ZD, would be, as we would expect, all of the vectors that have only polynomial coordinates. And our lattices are going to be the set of all the G's times the standard lattice, where the determinant of G has absolute value 1. And we call this space of lattices LD. So I'll let everyone stare at this for a quick second, since this may be a lot to take in. Okay, so now we have this, and let me show you a little bit about the geometry of this. So a way to look at the geometry of this field is that we can only obtain norms that are q to the power of some integer. So all of our norms are going to look like this. You could look at it as you have 0 in the middle, and then you have all of these spheres here, which are all the set of all the alphas that obtain a certain that have a certain absolute value. For example, these are all the alphas that have absolute value 1, q squared, and you notice that you cannot converge to points along different spheres unless if that point is 0. And let me show you how this looks like. So another way of saying this is if you have a non-zero point, then you can find a sphere around it, which is all a ball around it, which is all contained in its sphere, such as this point here or this point here. But you can converge to 0 along different spheres, but to other points you cannot. And this is going to be one important thing that enabled many of our proofs. So now let's talk about covering radii in this setting. For covering radii, we have the exact same definition, but now we take a function f, which take values in the vectors over Laurent polynomials, and it sends them to R plus, and it still has the same nice properties. And we say that the covering radius of a lattice lambda with respect to f is the smallest r, such that if we increase it slightly, we take the set of v's such that f of v is less than r, translated along lattice points, and we cover the entire space. So now let's give an example. Take the infinity norm, then f with respect to the infinity norm, and then the covering radius with respect to the infinity norm is going to be the same covering radius with respect to the convex body, which is O to the D, where OD is going to be this following ring of all of those Laurent theories that have only non-positive powers. So you could think of it as all of the Laurent series that have norm at most absolute value at most 1. And I'm cheating here because I did not define what's a convex and what is this convex body covering radius. So this is as we would expect in R. And also I did not define what's a convex body, which is a bigger problem in this case. So a convex body in the positive characteristic setting, this is something by Mahler, that the thing that satisfies all the properties of a convex body is going to be a linear image of this O to the D, of this ring. And now, a covering radius with respect to a convex body is going to be just as we would expect in the real case. That is, it's going to be the smallest r, such that if you take lambda and then you take this convex body C and you dilate it, how do you dilate? You dilate it by r times, but in our case, we'd have to multiply it by x to the power of log r. And then we translate this along lattice points, and we would cover all of our space of the Laurent series. So one of the theorems that I showed was that in this case, covering radii with respect to convex bodies are super simple, and that's because of the super simple form that we have of convex bodies. And these covering radii are going to be 1 over q times lambda d of h minus 1, where this is the dilation of lambda. And lambda d is going to be the d successive minima. So now let me explain what's this successive minima. This successive minima is if you have some lattice lambda, then you define lambda I of lambda to be the infimal r, such that lambda has I linearly independent vectors of length at most r, and you will have d of those. And this is for I equals 1 to d. So lambda d from previously came from here. And one known thing that we will need is that the product of these successive minima in positive characteristic is equal exactly to the determinant of this G in absolute value. Now, another way to say this, if you know this, is that the successive minima, they are orthogonal one to another with respect to ultrametric orthogonality. And I will remark that this is one thing that enables a lot of our calculations. And also, in the positive characteristic setting, you can find a basis over an R basis of lambda of successive minima. And this is another amazing fact and positive characteristic, which is not true in R. So I'll give a quick counterexample, which is you take the lattice lambda, which is given in this form. It's all of the set of vectors such that all the coordinates are either odd or even. Then you notice that the shortest linearly independent vectors, if you take D to be large enough, are going to be 2E1 up to 2ED, but now if you cannot, but this is obviously not going to be a Z basis because you cannot get those vectors with odd coordinates like this. So now I'm going to discuss the proof of my previous theorem. Sorry, I'm going a bit fast, but here it is, this theorem here. I'll discuss the proof of this theorem about the covering radius with respect to convex bodies. So what do I need for the proof? The first element that I need is this following theorem, that for every lattice, you could find an isometry, so that brings it to this form, that up to isometry, every lattice is of this form. It's x to the power of log of the first successive minima up to x to the power of the last log of the last successive minima, this diagonal matrix, times the standard lattice. Now I can prove my theorem. So the way that we do it is we first say we're just going to prove it for OD, and otherwise it's a linear image, so this is going to be left as an exercise for the reader. So now, since we notice that the covering radius with respect to OD is the same as the covering radius with respect to this norm, then it's going to, and this is invariant under SLDO. You notice this part here. Then by the previous theorem, we can take our earlier form and then just use that invariance. So it will suffice to prove our theorem only for lattices of this super easy form. So for these lattices, we just notice the following. We notice that if I take this vector here, this is going to be my shifting vector. And then I look at who is the closest guy in my lattice to this vector, then I'm going to get that it's going to be the vector 0. And therefore, for this one here, I have exactly this. So what does this prove? This proves that if I take that there exists a shift such that the best possible estimate is 1 over q times lambda d of lambda. And a way to see this is that this means that the covering radius is at least 1 over q times lambda d of lambda. On the other hand, we can do this kind of complicated computation of we take some vector and we represent it with respect to the basis, this basis here. And then if we take away all of these parts here, which are the polynomial parts, and we use the ultrametric inequality, which for those who understand, this is what we get. And then this concludes the proof. I'm going over it relatively quickly, but it takes some time to take in. So now I'll talk about another covering radius, which is going to be the Minkowski function. It's going to be the same one that we had in 0 characteristic. And this time we take the function n to be the product of the coordinates in absolute value. And then we take mu to be the exact same thing. Now let's just do a sanity check to check that mu is the exact thing that we wanted. So the first thing that we notice is that mu is indeed invariant under the group of diagonal matrices with absolute value of determinant equal to 1. So this looks good. Now you can do a quick computation if you're capable, or you can believe me, and see that mu of the standard lattice is equal to q to the minus d. So for our sanity check, everything seems to work as we want, and this gives us a good guess as to what should the upper bound of mu be if we follow the real case. And also, indeed, this is actually the upper bound. So in every dimension d, I was able to prove that mu of lambda is going to be bounded by q to the minus d. So let's ask about uniqueness. Is it unique? Turns out that it's not unique, and not only is it not unique, rather for every dimension d, we can find infinitely many distinct compact A orbits that correspond to number fields, such that mu of lambda is going to obtain that upper bound. And this is in contrast to what is believed is true in the real case. So I'll quickly sketch out how we proved the second part. For the second part, what we did was that we constructed a sequence of compact A orbits from number fields, and we did this using Dirichlet's unit theorem. And these ones, they exhibit escape of mass with a certain rate. And we used these rates in order to show that mu of these lattices must converge to q to the minus d. And then using this, we used that special geometry to show that if something converges to q to the minus d and it must obtain values only of the form q to the z, then at some point it has to be equal to q to the minus d. And that's concluded the proof of this. Now, I'll briefly literally sketch out how we proved in the first part about the upper bound. So the idea is the following. We take a set of lattices, which we call well-rounded lattices, and we prove that their covering radius is equal to q to the minus 1. Explicitly, it means that if you take the set of v's such that the maximal coordinate is at most q to the minus 1, and you translate it along lambdas, then you cover the entire space. Now, this proves that every lattice that's well-rounded must satisfy this inequality here, this equality here. Why? Because this set up here is contained in the set of v's such that the product of the coordinates is at most q to the minus d. And this shows exactly that mu of lambda is at most q to the minus d. Now let's see how this looks like. This is cooler than the written one. And this is the following. If you take this square here, which is a set of v's such that the maximal coordinate is q to the minus 1, and you translate and assume that if you translate the square along all these lattice points and you cover everything, then obviously the same should be true if you take any set that contains this square. In particular, if you take this star, which contains this square, then that should be true for that too. So now the next step that we do once we have these two steps is that we now prove that every diagonal orbit must intersect the set of well-rounded lattices. And then by the A invariance of mu, then we get that mu of lambda is going to be at most q to the minus d. So now I cheated and did not tell you what's these well-rounded lattices. So the well-rounded lattices is going to be the set of lattices which all of their successive minima are equal to one another, and they're all equal to 1. So now, by our previous theorem about these convex bodies, the covering radius of a well-rounded lattice with respect to this OD here is going to be 1 over q, because you'd have 1 over q times lambda d, but lambda d is 1, so that's what you get. And then you would get the first two steps. Now, as for the third step, I will not explain it, and this is the step that the well-rounded lattices intersect every single A orbit, but I will briefly explain an application of it to a different geometric invariant of lattices. And this is the Mordell function. So for the Mordell function, it's in a way a dual to Minkowski's convex body theorem. So we say that a box is going to be admissible for a lattice if the only non-zero lattice point that it contains is going to be 0. And in this case, the box, you could view it as what you would expect. It's going to be a product of a bunch of balls, or if you want, it's a set of v's such that the ith coordinate is going to be at most q to the power of ri. And this box, and now we can ask for every lattice, what is going to be the largest box which is admissible for it? And this is exactly what we call kappa of lambda, the volume of the largest box that's admissible for it, when the volume is just the product of these q to the ri's. And using our previous theorem, what we showed was that kappa of lambda is a constant function in positive characteristic. And it's moreover equal to q to the minus d. And this, I'll remark that it's very, very different from the real case in which kappa has a rich correspondence to the values to basically the rich structure of A orbits. So some of them are compact or arise from number fields or are algebraic or dense, and that they all would get different values in the real case. But here, this kappa does not distinguish between this dynamical information, unlike the real situation. So now let me just conclude with a few questions. Maybe if the audience has questions, you can also ask now. But I'll conclude with some questions here. So the first question that I would like to answer is, what's the lower bound? And in this case, it's easy to show that it's the generic value of our Minkowski function mu. We're able to show the upper bound, which is open in the real case, but not the lower bound, and that would be nice to know. And another thing that is well known is in dimension 2, we can show that this Minkowski function is actually trivial. This is not a very difficult result to show. And the question is this true in every dimension? at least in dimensions 3, one thing that we do see from computer computations of mu is that I have not been able to find a single lattice which obtains the value that is not the upper bound. So the question is, maybe this function is also trivial, like how kappa is trivial. And also we can ask what happens about other covering radii and positive characteristic, and how does this differ from the real case? And also, how does this correspond to dynamics? In particular, we took mu, which is invariant under the whole diagonal group. But what happens if we take, for example, a covering radius of something that is invariant under, let's say, a fixed one parameter diagonal flow or a unipotent flow? What can be said there? So now that I have a few questions up on the board, does the audience have any questions? Yes.
Do you have a conjecture on what kind of kappa could be used to distinguish, like?
You mean a geometric invariant that distinguishes between
Yeah. So like the dual problem.
Okay. That's actually a good question. I don't have an idea about that at the moment, but I think that somehow geometry and positive characteristic seems to be almost, what is that word again? It seems to be almost degenerate. So one question is, is there one that even exists? Any more questions?
What, I don't know why it's doing this. Can you say anything about, because you took like this finite fields,
Yes.
Can you say anything about like Puceau series where you allow like real numbers within X?
What do you mean by you allowed real numbers? You have
like instead of working with FQ, you work with you replace the FQ with the real numbers. And then those are the field of Puceau series, but you still have a positive.
Okay, so actually when you do that, it is well known that, so one thing that's well known, I think, is that Minkowski's conjecture does not hold in those. I think that there is a result, there's a very, very old result that shows something similar when you replace when you replace FQ with Z. So I assume that it should be similar for Puceau numbers.
So you showed us this well-rounded lattices.
Yes.
The successive minima are all equal to
Yes.
1. So these are the only ones that can have the...
That can have the upper bound. Our conjecture currently is that every lattice gets that upper bound, but those are the only ones that have the covering radius with respect to OD to be equal to 1 over Q. But also another thing that I should remark is that the result that we have about the well-rounded lattices intersecting every A orbit, that is actually true in the real setting. When you say that the well-rounded lattices in the real setting, they all have this, all their successive minima are all equal to one another, but in the real setting, they are not necessarily all equal to 1. And that's because Minkowski's second theorem, unlike in the positive characteristic setting, does not have an equality, rather a double-sided inequality. And that result about every well-rounded lattice intersecting the A orbits, that's a result by Omri Solan, I think from 5 years ago.
Okay, then I think we can thank the speaker.
So we are here. Good afternoon, everyone. We are starting the afternoon session. And just a quick reminder that at 5:30 there will be a panel and a discussion panel and mentoring, etc. And after that there will be drinks. So we start with Natalia Jurga, and her talk will be about domination in matrix semigroups.
Thank you. Thanks for the introduction. Thanks to all the organizers and for inviting me to speak. And everyone for coming, of course. So yes, I'll be speaking today about some problems me and my friend and collaborator Argyris Christodoulou have been interested in. We've actually been discussing Christodoulou from the Aristotle University of Thessaloniki. Yeah, we've been discussing these problems on and off for a few years, but we actually don't have, so we've got some partial results, but not enough to kind of give a nice story today. So I decided instead to kind of give some of the inspiration behind our work and mention some of the kind of results we're working on while I go along. Okay, so far we've in some of the talks this week we have heard about some moduli spaces, some parameter spaces, especially the Mandelbrot set yesterday. So this talk will also be about a particular parameter set. So the parameter set I'll be interested in is SL2R to the n, or SLDR to the n, although I'll mostly be focusing when d equals 2. And yeah, so basically each parameter within here, so a tuple of n matrices from SLDR, so d by d matrices with determinant 1. Each of these basically will correspond to some dynamics. You can think of this as, I'll go through this in a second. You can think of this either as like a semi-group generated by these matrices. So group generated by A1 through to AN, acting on d-1 dimensional real projective space, which in the case I'll concentrate on, d equals 2 will just be on the circle. Another way, if you prefer, so this is kind of my entry into this. So I kind of came into this area through studying Furstenberg measures associated to these semi-groups and particular fractal sets which form the support of these stationary Furstenberg measures. But if you prefer, you can think about these as locally constant linear co-cycles over the shift instead. Okay, so basically to each parameter from here, we have some sort of dynamics. And what I'll be interested in is in trying to understand the topological properties that certain dynamics have within this parameter space. Okay. So, okay, and so the reason why I like this parameter space is because within it you can kind of see a lot of different types of dynamics. So you can see hyperbolic dynamics, you can see parabolic dynamics, elliptic dynamics, you can see non-conformal and conformal if you vary the dimension. And so it's kind of a nice sort of playground in which you can explore what these different dynamical properties look like within the whole space. Okay, so there'll be no measures in my talk. So all of these properties will be purely geometric or topological properties, and the property we'll particularly be focusing on is the property of uniform hyperbolicity. Okay, so this is when d equals 2. In more general, this is known as one domination, which is why I wrote that in the title. But since then, I decided to just mainly focus on the 2D setting. Okay, so uniform hyperbolicity. So what is this in this setup? So we have kind of two equivalent definitions for this. So one is stated in terms of the norms that you see as you make this semi-group grow. So uniform hyperbolicity, so this is a definition now. So there exists a lambda bigger than 1, such that for all I1 through to IN, so words in 1 through to n to the power n, the norm of AI1 through to AIN is growing at this uniform exponential rate, lambda to the n. Okay, so there's also an equivalent definition, which is a geometric definition. And this is the following. So if there exists okay, I'll just write down the words and say what it means. A strictly invariant multicone in LP1. Okay, so multicone. So this is just a finite union of open subintervals of projective space. So this is just a circle. Okay, so if you have, so a multicone is a finite union of open intervals, and a multicone is strictly invariant under the action of these if basically the union of the images of this multicone under the AIs is their closure is contained within your original multicone. Okay, so a simple example. Okay, so notice that from this definition, maybe it's a bit difficult to check whether a particular tuple is uniformly hyperbolic, whereas this definition makes this a lot easier. So for example, if you take a finite, let's say two positive matrices, strictly positive matrices, then you could just take the multicone to be the cone, this now, a cone corresponding to all positive directions. Then by positivity of your matrices, these will be, let's say, so I'll be drawing some pictures. So I'll basically a hyperbolic I'll represent by an arrow like this so the arrow is pointing towards the attracting fixed point, and this one is the repelling fixed point. Okay, so if you have two positive matrices like this will map this interval here inside here, maybe into an interval around the attracting fixed point here, and then this one will map this interval into another interval around the attracting fixed point here. Okay, so positive. So a finite set of strictly positive matrices are an example of a uniformly hyperbolic system. But of course, you can have matrices which you can have uniformly hyperbolic matrices which don't preserve a cone but preserve a multicone. So for example, if I took these two hyperbolics and I ensured their norms were sufficiently large, then if I took this multicone, so the union of this interval here and this interval here, if the norm of this matrix is sufficiently large, so it will send this inside itself and then this all the way in here, and then similarly for the second one. Okay, so basically with these pictures, all you have to understand is that when you act by this matrix, let's say A, points will always move away from the repelling fixed point and towards the attracting fixed point. Okay, and so what does an intersect? So yeah, I know less about groups. So I'm working with a semi-group here. So maybe there's a difference there. But yeah, you certainly want that there needs to be distance between these fixed points here, and the norm needs to be sufficiently big. And as long as those two things are satisfied, the system will be uniformly hyperbolic. Okay, so this equivalence here in dimension 2 this is due to Avila, Bocchi, and Giocos. So I'll be writing that a few times today. So I'll abbreviate this by ABY. And then there's kind of, in the one-dominated setting, there's something analogous to this. And that is due to Bocchi and Gourmelon. Okay. Okay, so okay, so what does this, yeah, so this uniform hyperbolicity, so I'll call the hyperbolic locus okay, so I'll denote it by H. Hyperbolic locus will be the set of all uniformly hyperbolic tuples. And this is kind of the main object I want to study today. Okay, so the kind of a basic question is, what does this look like in parameter space? Okay, so I'll draw a picture here and I'll actually leave it on the board, and then as we understand it more, I'll maybe add some things. Okay, so so what do we know? So firstly, we know that this is just a kind of simple observation that this is an open set because this is an open property here. If you perturb your matrices a little bit, you can still find a multicone very close by. So it's certainly an open set, but it's not connected. So actually, before okay, let me first say, okay, if we just have one matrix, n equals 1, what does the picture look like? Well, I've got my uniformly hyperbolic tuples are just the hyperbolic matrices. And then what else do I have in parameter space, which now is SL2R? Well, I have my elliptic matrices, and then the boundary between them will be parabolic matrices. Okay, so this is the picture when n equals 1. So now when n equals 2, well, n bigger than or equal to 2. Okay, so by what I just said, it's open and but not connected. So we actually have H consisting of some connected components. Within each of these components, the rank of my multicone is constant. And in fact, even if you just have n equals 2 here, so you're just looking at pairs of matrices, you can find systems which preserve a multicone of arbitrarily large rank, let's say some big number C, but don't preserve a multicone of any smaller rank. And so in particular, there are infinitely many of these connected components. Yeah, so there's some other things we know. For example, for pairs, we know that, okay, so in the Mandelbrot set, we had something similar, right? But in that case, these components are actually touching. In the pairs case, we know that these multicones, these components here, they're not touching. So yeah, we actually have something like separated as we have here. And yeah, so I've been meaning to like plot this, like using a computer. So I don't know if anyone's come across Schottky space or like the Riley slice. The Riley slice is like a slice of Schottky space, and it really looks something kind of fractal like the Mandelbrot set. So I imagine this would look kind of similar. Okay, so this is what H looks like. Now, what's in the complement of H? Okay, so what's in this C around here? So now let me define the elliptic locus to be the set of all tuples which generates a semigroup which contain an elliptic matrix. Okay, so as soon as you have an elliptic matrix in your semigroup, you know automatically you can't be uniformly hyperbolic because any power of that, its norm will not be growing. So certainly the elliptic locus lies in the complement of H. Okay, so you can kind of think of this as a C around. Again, this is an open property. So this is due to Avila, I think. So it was in a paper of Yokos, so I credited to Avila. And it's also, so unlike the hyperbolic locus, it is connected. So this is, again, it appears in the paper of Avila, Bocchi, and Yokos. Okay, so this is an open and connected set which lies in the complement of H. Okay, open and connected. Okay, so now let me state maybe 3 questions I want to focus in on today. So firstly, okay, so we've got our hyperbolic locus, we've got our elliptic locus. So first, a basic question is there anything else? So obviously we've got like the boundary here, but is there anything else? So kind of question 1. Question 1 is the boundary of H union E equal to SL2R to the N. Okay, then a second question, if I have time. Okay, so we know that in the hyperbolic locus, we have these nice dynamical properties. We have this nice growth of the norms, and we have this geometric property as well. So maybe another question is, okay, so here we know that there is at least one elliptic which violates the uniform hyperbolicity, but can we say anything about maybe some weaker type of hyperbolicity that we see in here? Okay, so here, if I have time, I'll talk about some conjectures by Bocchi and Gourmelon. And then thirdly, so the question I'm particularly interested in is in understanding the boundary, basically the boundary of the hyperbolic locus. So question 3 is what happens on the boundary? Okay, this is slowly becoming a mess, so, but okay. Question, this one. Oh, this one. Oh yeah, okay. Yeah, so the question is essentially, is the hyperbolic and the elliptic locus dense in parameter space? Oh yeah, sorry, closure. Yeah, sorry. Yeah, closure. Is the closure of H union E equal to SL2R? Okay. Okay, so first let me go to that question. Yeah, so the answer to this is yes. So by Avila, no, actually, sorry, I think this was the result in the Yokos paper, which was accredited to Avila. Indeed, this the union of the hyperbolic locus and the elliptic locus are dense in ramped space. So this is kind of like an analog of, so you can think of this union as like being the stability locus, because these are both open properties, and so these form like a stability locus for this parameter space. So in this sense, this is kind of like an analog of, for example, the Manier-Sad-Sullivan theorem for the density of the stability locus for rational dynamics, rational maps. So the proof is, it uses this trick where you take some hyperbolic system and then you put in some rational in between all of the matrices, like the same, not rational, some elliptic in between all the matrices, and then you sort of complexify the problem. And yeah, basically I won't go through the proof, but it uses this trick with these inserting these elliptics in between the matrices. So people have tried to prove this result in the dimensions bigger than or equal to 3, but somehow this trick just doesn't work anymore. Several people have tried, and so kind of the analog of this result in higher dimensions is still unknown. Okay, so I'll just speed through that one. So next, let's talk about this, sorry, not Bocchi-Gourmallon, Bocchi-Fayad conjectures. Okay, so the second question here was about what's really happening in the elliptic locus. So we know that there is some elliptic, which is kind of ruining any form of hyperbolicity for us. But the question is whether we still have hyperbolicity for some sort of large subset of this semigroup. Where large, again, I don't have any measure, so it's not from like a measure theoretic point of view. But for kind of many, I guess the question is whether for many words, many elements within this semigroup, we are seeing some hyperbolicity. Okay, so I'll restrict the pairs now. So I'll take n equals 2. I'll fix some, okay, I'll consider A1 to be a hyperbolic and A2 to be an elliptic, so that this pair A1, A2 just trivially belongs to the elliptic locus. And let me state a definition. So we'll say that A1 resists A2 impurities if there exists some epsilon and lambda positive such that if you take any word in these A1s and A2s, this up. So if you take any word in these A1s and A2s, where the proportion of elliptic elements, so the proportion of A2s is at most epsilon, then you recover exponential growth of your norm. So this is bigger than or equal to lambda to the I guess here lambda should be bigger than 1. Whenever I contains at most epsilon times the length of the word I, A2s. Okay, so let's look at this. So first, I just want to make an observation, which is that we can construct a very simple example, which shows that this property, so this resisting impurities property, doesn't hold throughout the elliptic locus. So if I take A1, for example, to be this matrix here, and A2 to be this one here, then if I consider, say, A1 to the n, so I'll have 2 to the n here, half to the n down here, and then this will, so A2 here is going to kind of switch the 2.5. And so when I multiply this product through together, I'll just get that the norm is equal to 1 for all n and n. And so A1, A2 does not, so maybe A1 does not resist A2 impurities. But somehow this example, it's quite special. And so the question, the conjecture of Bocchi and Fayad was that somehow the set of A1s and A2s, such that A1 does resist A2 impurities, should have full Lebesgue measure. So A1, A2 in set of hyperbolic elements times elliptic elements, which resists impurities, has full Lebesgue measure. Okay, so this is kind of a difficult question because it's you really need control over all words which have a certain number of A2s, and not just typical words. So you can't kind of use methods of ergodic theory, for example, to tackle this problem. So far, this conjecture has not been proved. It's not even known whether this set has positive measure. So Avila and Roblan have some progress towards this conjecture. So they've shown that the conjecture holds if instead of having at most epsilon times the length of your word elliptic elements, you allow at most epsilon times the length of your words over log length of your words, log length of your words, sorry, A2s. Okay. Yeah, so I don't know. I find this problem quite interesting. I haven't managed to prove any improvement on this yet. Okay, so finally, let me go to the third question, which is about the boundary of the elliptic locus. So this is something we've been working on. We're working on at the moment. So what is on the boundary of H? Okay, so let me go up to this picture here. Okay, so let's say we're in the hyperbolic locus here, and then I'm kind of like perturbing, I'm traveling along some path, and I'm trying to hit the boundary here. So there are kind of a few trivial ways that one can do this which spring to mind. So firstly, if I have, let's say, two hyperbolics like this, A and B, then I could, so from the point of view of fixed points, there are kind of three things I could do. So I could perturb these fixed points in until B becomes a parabolic. And as soon as I have a parabolic here, again, I know I'm not in the hyperbolic locus because the norm of that parabolic will grow polynomially, not exponentially. Okay, so this is kind of one way. Second way is, okay, if I had instead this picture here, so where my hyperbolics were going in opposite directions, then I could kind of perturb the fixed points so that the repelling fixed point of this one hit the attracting fixed point of this one. Okay, and then again, I see that uniform hyperbolicity fails here because I cannot construct a strictly invariant multicone for this system. And then there's one more kind of trivial way I can think of, which is, again, if I'm, let's say, in this situation, and now instead I just kind of weaken the let's say these are two positive matrices, I just weaken their hyperbolicity. So I'm taking their norm down towards 1. And then basically, at some point, one of these matrices will hit the identity. So essentially, you lose the fixed points altogether. Okay, so so Avila, Bocchi, and Yokos, they showed that essentially these three mechanisms for traveling towards the boundary are the only ones which are possible. Okay, in a very concrete way. So if you hit the boundary, either okay, so then I can so I started in some multicone. Oh, I just dropped out. Okay, so I started in some multicone where the rank I started in some component of the hyperbolic locus, within this component, all the uniformly hyperbolic tuples have constant rank for their multicones. And so to each component, we can associate a certain number, let's say C. Okay, and that's actually this irrelevant. Okay, sorry. So you started within some hyperbolic component, and to each hyperbolic component, I can get a number C, such that if I look at all products of length n, so basically I generate my semi-group up to times C. Okay, so then within here, I will either, if I'm on the boundary, I'll either find A, which is the identity, or I'll find A, which is parabolic, or I'll find A, B, and C such that A maps the attracting fixed point of B to the repelling fixed point of C. Okay, so these are the only three options that occur here. So yeah, so the first option there was essentially corresponding to this one here. The second one was this one here, where I turned the hyperbolic into a parabolic, and then the last one was here. So it's not exactly just those three cases, but you can have attracting fixed points being mapped to repelling fixed points. And also these things can not appear in the first few levels, but they will appear within some uniformly bounded time, where that time depends on your component. Okay, so yeah, from the point of view of fixed points, this kind of characterizes the boundary of components, of hyperbolic components. So one thing we've been working on is trying to do something similar in higher dimensions. And this is already, there's kind of like quite a big obstacle in the way from the get-go, because the way this proof works in the case where d equals 2, you're really depending on the fact that when you have this multicone, let's say we have multicone consisting of two intervals here, the number of extreme points in these, in your convex components of your multicone is finite. Just it's forced by the geometry, of course. Any interval has two extreme points. But now when you go to the higher dimensional setting, your multicone is like a finite union of cones, but those individual cones aren't necessarily convex polytopes. And this poses a problem because the way that this proof works is you basically start at an extreme point and then you kind of iterate that extreme point back in a certain way under elements from your semi-group, such that the extreme point maps to another extreme point. And then you do this enough times, and then eventually you need to repeat one because you've only got finitely many. And from once you do that, you can build these matrices A, B, and C. That's how the proof works there. As soon as you have potentially, cones in R2 which aren't convex polytopes, this trick doesn't work. Okay, so that's kind of one way of characterizing boundary. So from a more like broad point of view, okay, so from a more broad point of view, what do we know? So in the case that you're just looking at pairs, what we know is that the boundary of the hyperbolic locus are just the union of the individual boundaries of hyperbolic components. And we know, so this is one point, and we also know that the elliptic locus and the hyperbolic locus share the same boundary. And so this common boundary is kind of like the bifurcation locus for the system. So where you go from hyperbolic dynamics to elliptic dynamics. On the other hand, when n is bigger than or equal to 3, both of these things fail, are no longer true. So on the first point, so this was a result of Christodoulou, Jakes, and Short. So as soon as you have more than 3 matrices, so n bigger than or equal to 3, then I rubbed out the picture, but we had these hyperbolic components. In this case, we know that these hyperbolic components can actually accumulate, and that point is in the boundary of the hyperbolic locus. And kind of from a geometric point of view, what that point will do is it'll generate a purely hyperbolic semigroup, so no parabolic elements in there or anything like that. And it won't preserve any finite multicone, but it'll preserve like an infinite version of a multicone. And now the second point also fails. So for n bigger than or equal to 3, what we know is that the boundary of the elliptic locus is strictly bigger than the boundary of the hyperbolic locus. And this is by considering, I think the example, so this actually answered, this again was by Jakes and Short. This answered an open question of Yokos. And the example, I think, looked like this. So you have 2 hyperbolics with a common attracting fixed point, and then another hyperbolic with its repelling fixed point at that common point. Okay. And then finally, so these are kind of like 2 different perspectives about what is happening on the boundary. The third perspective that we're kind of working on at the moment is basically, okay, so this is telling us like how to characterize the boundary from the point of view of the fixed points. This is kind of telling us, yeah, what the boundary looks like and how it interacts with the boundary of the elliptic locus. And so a question I've been interested in is whether you can recover any weaker form of hyperbolicity in the boundary okay, so question, do tuples in the boundary possess any kind of weaker hyperbolicity properties? So my original motivation for this came from the point of view of fractal geometry. I've been interested in trying to understand the limit sets that you get in the projective space corresponding to these semigroups. And so the kind of like fractal geometry for uniformly contracting iterated function systems is well understood. Whereas these, so if you could somehow relate these kind of boundary semigroups to something uniformly hyperbolic, which still captured most of the geometry, this would be kind of useful. So again, in the two-dimensional setting, what is known? So there's kind of two things you know. So you can show that the identity does not appear in most of the boundary semigroups. So this can be made precise. Essentially, there's a finite set of hyperbolic components where on the boundary, the identity does appear in the semigroup. So essentially like the ones which, so you have hyperbolic components which preserve a single cone. And if you go to the boundary of those, you could see the identity there. But on all of the other components, the identity doesn't appear, because if it did, it would ruin the multi-cone structure along the way. And then using this, you can then kind of use some quite deep hyperbolic geometry to deduce that you can find some matrix B within your semigroup such that, okay, so you'll have like a forward limit set corresponding to your semigroup, which will be maybe some Cantor set here. And then you'll have maybe another color, a backward limit set as well. And basically you can find this matrix B in your semigroup so that this attracting fixed point is contained in some interval which doesn't intersect the backward limit set, the repeller. And similarly, the repelling point is contained in an interval which does not intersect the forward limit set. And once you have this, you can basically build a very nice induced system. So consider BA where A, so all elements BA where A is coming from the semigroup. And we can show, and just by this property, this countable, let's say, induced system is actually uniformly hyperbolic, because, you know, if you take any A coming from the semigroup and you apply some point from this interval, you apply A to some to the point from the interval, because this is separated from the attractor. We know that point under A won't land in here, or maybe move somewhere else, but it won't land in here. And then once you apply B, because you're not in this interval here, then you know if you apply a sufficiently large iterate of this, this will land back in here. And so so maybe you need some big M here. And you know this is uniformly hyperbolic. And so as I said, this is very useful, for example, in fractal geometry, because you can associate your original system to a uniformly hyperbolic subsystem. And what we've been doing is to try to make this work in the higher dimensional setting. The issues there are, there's a number of issues. So the non-conformality is an issue, especially its interplay with kind of the non-uniform hyperbolicity. And secondly, you don't have any hyperbolic geometrical tools, which are kind of used in actually a very intricate way for this part of the proof. So yeah, okay, I'll stop there. Thank you.
Thank you, Natalia. Are there any further questions? Please.
Multi-cone in higher dimension, they're not unions of polyhedrons. I mean, the cone over polyhedrons. So how does it look in general when, so uniform hypertext?
Yeah, so what is known is that they're a finite union. So in projective space, they're a finite union of convex sets, but nothing is known about what these convex sets look like. And basically, yeah, so like, I guess the issue for us with that result was a priori, yeah, you could have kind of like a convex hull which has like infinitely many extreme points, if that makes sense. Yeah, so in the yeah, it's not really understood actually what those multi-cones look like at all. Yeah.
So I know you said no measures, but if you were to look at like some measure on your finite set, is resisting impurities, like, are there examples of things that don't resist impurities that have positive Lyapunov exponents?
Are there examples of things which
in the elliptic
which don't resist impurities but have a positive Lyapunov? No, I think oh. So I guess I gave this example.
Right, but the example you gave has 0, which is why I was wondering.
I guess so for any measure, I guess it depends what measure you put on it.
I mean, because it's just as long as you don't assign one of them 0 measure, that measure will always have 0 Lyapunov exponents.
Yeah, I'd have to think about that. Yes, good question.
Okay. So next talk will be by SeulBee Lee, and it's about approximation by rational numbers of some parity types.
Thank you. Thank you for giving me the opportunity to give a talk. I'm very happy to come back to Pisa after my postdoc in Centro di Geology. And today I'd like to introduce the best approximation property with certain parity conditions. Yeah, it is well known that a relation between the regular continuous fraction and best approximation property, and also it's well known that a connection between regular continuous fraction and a geodesic flow on the modular surface. So I'm interested in generalizing this kind of property. So it's a kind of generalization. And this is joint work with Dong-Han Kim from Dongguk University in Seoul and Lingmin Liao from Wuhan University. Okay, so let's consider a rational approximation to a real number x. For example, this is a golden ratio, and we can consider a decimal approximation, and we have a finite truncation of decimal approximation. Of course, it converges to x, but the first one is a best approximation, but the second and third one are not best approximations in the following sense. Yeah, we already seen the best approximation in the Sunnis talks. Yeah, so what is the best approximation? When we measure the quality of the approximation, it is reasonable to use the distance between x and p over q, x and p over q. So a rational p over q is best approximation of the first kind if the distance between x
and P over Q is less than the distance between X and A over B among the rationals whose denominator is less than or equal to Q. So in this example, in this example, 1 is best approximation because it is the closest integer from X. And the 1/2 is the second best approximation because it is the rational, the closest rational whose denominator is less than or equal to 2. So this third one is 2 over 3, and 3 over 5 is also a best approximation, but 3 over 4 is not a best approximation because this denominator is larger than 3, but is farther than 2 over 3. So, okay, then, yeah. So regular continuous fraction is an algorithm to finding all the best approximations. So every best approximation of the first kind is a principal convergent or an intermediate convergent of the regular continuous fraction. So let me explain what are they later. And also Lagrange proved that every best approximation of the second kind is the stronger version of the best approximation. It is a principal convergent of the regular continuous fraction and also the converged wholes. So in the definition of the first kind, we use to measure the closeness between X and P over Q, we use the absolute value of Qx minus P instead of the distance from X and P over Q. So yeah, actually we already seen this expression in the talk in the morning session. So you can see, you know that it is important then. And also this inequality implies the first inequality. This one, we can easy to check that this inequality implies this inequality. So second kind best approximation is the stronger version of the best approximation. Okay. So yes, we see that what is the regular continuous fraction. So this is A0 plus 1 over A1 plus 1 over A2 plus and so on. And here A0 is an integer and AN is a positive integer. So, and every real number can be expressed by the regular continuous fraction. So we can find it inductively in this way. So A0 is the integral part of X, and A1 is the integral part of 1 over X minus A0. A2 is the integral part of 1 over X minus 0 minus A1, and so on. So then by Euclidean algorithm, if X is rational, then this algorithm stops in finite type. Then if X is rational, then it has a finite form of the regular continuous fraction. But if X is irrational, then AN will be the infinite sequence. So we have infinite type of continuous fraction. Then, yeah, so we know that the finite truncation of the continuous fraction gives best approximation. So we denote it by Pn over Qn, and we call it a principal convergent. So this sequence converges to X, and it looks like this. So P0 over Q0 is A0. So it is on the left side of X, and P1 over Q1 is A0 plus 1 over A1, and it is on the right side of X. And it appears alternatively left and right, and it closer and closer. So I recall the Lagrange theorem as follows. So the set B of X is the set of best approximations. It's equal to the set of principal convergent Pn over Qn. So there are at least three versions of proof. So the first proof is algebraic proof. And yeah, in the famous book of continuous fraction written by Kinchin and another book written by Rocket and Switz, they explain this algebraic proof, and the key lemma, I mean key proof of, key property of the algebraic proof is that those two consecutive principal convergent, the distance between them is too small. Explicitly, this distance is 1/, Q2n times Q2n plus 1. So it's key property. And also Erwin gave geometric proof using the lattice G square. So we can interpret the best approximation property by the approximating lattice point of the line. So we will see this lattice argument later. And also Schott gave the geometric proof using Ford circles. So Ford circles is a collection of the Horo cycles based on rationals, and their Euclidean radius is 1/2b square. So it has many beautiful properties related to Diophantine approximation, but I will not explain this in this talk. But we will see the fairy graph later, and it is kind of a dual of the collection of Ford circles, so we will see it. And for the best approximation of the first kind, we need intermediate convergence. So let me explain what is intermediate convergence. First, Pn and Qn, I mean the denominator and numerator of principal convergent satisfy this recurrence relation. So Pn is 2an times Pn minus 1 plus Pn minus 2, and Qn satisfies the same recurrence relation. So instead of an, we put k is the number between 0 and an. Then we have the intermediate convergent, Pnk over Qnk. And if we fix n, then this series of intermediate convergent appear between Pn minus 2 over Qn minus 2 and Pn over Qn. So yeah, it's actually intermediate. So okay. So and we can understand the intermediate convergent as a best signed approximation property. So we defined it. We defined the best signed approximation. So a rational P over Q is the best signed approximation if any rational A over B such that B is less than or equal to Q, and its linear expression bxa and bx minus a and qx minus p has the same sign. So we only consider the rationals on the same side from x. And it satisfies the same thing, the linear expression, the value of the linear expression. I mean, the absolute value of the linear expression is smaller than the absolute value of the linear expression of A over B. Then we showed that the set of best signed approximation is exactly the same to the set of intermediate convergent. Okay, so let me briefly summarize what I told you with this example. So we consider pi, and the integral part of pi is 3, and we know that 1/8 is smaller than pi minus 3, and it is smaller than pi 1/7. Maybe one can calculate it in your brain, not me, but and then so pi is starting from 3 and 1/7, and then what is the third one? It is more complicated to calculate it. So it's 1/16 pi minus 3 minus 7. Yeah. So even if this AN is the index is too small, really small, but it is not easy to calculate the AN. So this is 15, so on. Then we have on the real line, we have pi here, and this is P0 over Q0, which is 3/1. And here we have P1 over Q1. This is 22/7. And P2 over Q2, which is 3 plus 1/7 plus 1/15. This is 333/106. And we have a bunch of intermediate convergent. For example, here we have P2, 1, Q2, 1, which is 25/8, and we can have it by vary sum of these two things. So vary sum means that we sum numerators and some denominator separately, and then we have 25/8, and so on. And we have P2 14 over P2, Q2 14 is 311/99. So in this talk, I will define the best approximations with the parity condition, which means that we give a condition on the numerator and denominator as even or odd. And we characterize the set of best approximation with the parity condition by lattice argument. And also, I will introduce a new algorithm detecting all the best approximation with the parity condition by coding of geodesics on the hyperbolic plane. Okay, so let's consider symbols 0, 1, and infinity. So this 0 for me is 0/1. So it stands for even over odd. And 1 is 1/1. So it stands for odd over odd. And infinity is 1/0 for me, and it stands for even odd over even. So we only consider the irreducible form of the rational, so we don't have even over even. So we divide the set of rationals by those three sets. So Q0 is the set of even over odd, Q1 is the set of odd over odd, and Q infinity is the set of odd over even. And also we use this Greek letter alpha, beta, gamma, representing 0, 1, infinity, because I don't want to write the symmetric statements 3 times, so I use it. And Q alpha beta is the union of Q alpha and Q beta. Then the best alpha rational approximation defined by the best approximation among the alpha rational Q alpha. So if P over Q is a alpha rational and it satisfies this this condition among the rationals in the alpha rational set, then we call them a best alpha rational approximation. And also the best alpha beta rational approximation use Q alpha beta. Okay. Then we show that the set of best alpha rational approximation is characterized by the intermediate convergent. So the set of best alpha rational approximation is the same as the set of intermediate convergent contained in Q alpha. And also B alpha beta is the set of best alpha beta rational approximation. And it is the union of the best approximation in the Q alpha beta and the set of pure intermediate convergent, which means that it is intermediate convergent, but not a best approximation. So pure intermediate convergence satisfying the condition gamma. Yeah, gamma is a symbol which is not alpha and beta. So condition gamma means that P over Q is the alpha beta rational, and there exists gamma rational which satisfies the absolute value of the linear expression is smaller than or equal to the absolute value of Qx minus P. So in some sense, A over B defeats P over Q, but it is not alpha beta rational. Okay. And to show this statement, it is useful to consider the best approximated lattice point. This V is a primitive vector, primitive lattice point PQ. And in this section, I use T instead of X because it is confusing with the X coordinate zone. And we have this lattice Z square, and this is the line Y is equal to 1 over T X. Then we choose primitive vector PQ, and this distance is the absolute value of Qt minus P. So we can define the best approximated lattice point with this figure. So we consider the parallelogram PQT, which is has the endpoint V and minus V, and these two edges parallel to the X edges, X axis, and these two edges parallel to the Y is equal to 1 over TX. Then if P over Q is a best approximation of T, if and only if this parallelogram does not contain a lattice point except for V and minus V and 0. Also, we consider the positive parallelogram looks like this. And if P over Q is signed best approximation, which means that the intermediate convergent, if and only if this positive parallelogram does not contain the lattice point except for V and 0. And also we can define the parity type best approximated lattice point by using the sublattice with covolume 2. So there are three sublattice with covolume 2. First one is lambda 0, whose X coordinate is even, and lambda 1 is the collection of the point who P plus Q is even, and lambda infinity is the set of points whose Y coordinate is even. So I draw the point of each sublattice as this figure. So if P over Q is best alpha rational approximation, if and only if this full parallelogram does not contain primitive vector of lambda alpha except for V and minus V and 0. And also P over Q is contained in the best alpha beta rational approximation if and only if this full parallelogram does not contain the primitive vector in lambda alpha or lambda beta except for V minus V 0. Okay. Then the first assertion of the theorem, B alpha is equal to S intersection Q alpha, is interpreted as follows. So the PQT intersection, the primitive vector of lambda alpha is V minus V0 if and only if the positive parallelogram intersection Z square is V and 0. So it is easy to see that, for example, if we have the W in the full parallelogram and this W is alpha lattice point, then we consider the middle point between these two W and V, and W and V satisfy the same parity conditions, so U should be the integral point, and U is contained in the positive parallelogram. So we have the one direction, and also the other direction is obtained by the way we can assume that U exists here, and then we define W as follows, and W and U satisfy the same parity conditions. So it is easy to see that this property by using the lattice argument. In the last section, let me explain some continued fraction expansions related to the parity type best approximation. So Short and Walker defined best zero infinity rational approximation, but they use different name, but anyway, so they defined it and they showed that the set of best zero infinity rational approximation is the same to the convergent of the even continued fraction. So here, convergent means that the finite truncation of the continued fraction, and even continued fraction means that the continued fraction with the positive even partial quotient, positive even an, and each numerators can be +1 or -1. And also in our previous project, we construct continued fraction map, and it generated all the best one rational approximation. So we call this continued fraction odd continued fraction, because all the convergent are odd over odd. So we constructed it in this way. So we consider the jump transformation of the roaming map with respect to this interval. So roaming map is a slowed down version of the even continued fraction map, and jump transformation is an acceleration, a way of to obtain the acceleration of original interval map. So this is the definition. It looks like it looks similar to the first return map, but yeah, M is the first return time to I, but in the jump transformation case, we iterate it once again. So we have this map. Then yeah, we have this result. But in this project, we introduce another type of expression, and it is a boundary expression of the hyperbolic plane. So yeah, it is. We know that many examples related to the boundary expansion of hyperbolic plane and the continued fraction, but in our expansion is not really. We can find it in the future, but in this now we don't know it. Anyway, so boundary expansion of a hyperbolic plane. So we consider the hyperbolic plane as an upper plane model. And then the boundary of the hyperbolic plane is the extended real line. And and then the oriented preserving isometries is the Mobius transformation. So Mobius transformation is a linear fractional map AZ plus B over CG plus D. And this ABCD is a matrix with the determinant 1. And also we consider the oriented reversing isometries with the matrix with determinant -1 and the complex conjugation of the linear fractional map. And series elaborated the connection between the regular continuous fraction and the geodesic flow on the modular surface. And to explain this connection, she used that Ferry tessellation. So Ferry tessellation is the image, PSL to the image of T, and this T is an ideal triangle with vertices infinity, 0, 1. So series explained the connection between the cutting sequence of the Ferry tessellation of a geodesic G and the regular continuous fraction of the endpoint of G. Yeah, so we can see the connection between the modular surface and continuous fraction. I mean, one evidence is that PSL to G is generated by the translation by 1 and the inversion. So yeah, we know the ingredient of the regular continuous fraction is just adding the integer an and inversion 1 over x. So we can expect the connection here. And also Boca and Merriman explain the connection between the even continuous fraction and the same cutting sequence of O. Yeah. So also we can see because the T, the ideal triangle T is the fundamental domain of the zeta group, and this zeta group is generated by the translation by 2 and the inversion. Okay, so in in our new expression, we also use Ferry tessellation. So and we consider the triangle group associated to T, so which means that delta is generated by H0, H1, H infinity. So H0 is a reflection by this line, and H1 is reflection by this line, and H infinity is reflection by this line. And yeah, I draw a picture as a disk, but we only consider the upper plane model. So I colored this line as in red, and this line green, and this line blue. And we consider the delta, the triangle group image of this triangle. Then we have a colored Ferry tessellation. And then we think about okay, let's consider x is between 1/2 and 2/3. And we think the geodesic from infinity to x. And we code all the colors, which is corresponding to all the symbols, of arc, which is the geodesic passes through. So if x is between 1/2 and 2/3, then we start from the symbol infinity, and then it passes through blue, so we code 0, and red, so you code 1. So this x, the delta expression of this x starting from infinity, 0 and 1. So then sorry, yeah, okay, so our theorem is that we can detect all the best approximation and best alpha rational approximation and best alpha beta rational approximation by the delta expression. So, yeah, let me stop here. Thank you.
Thank you. Thank you very much. Do you think you can reach results a la Baladi Valley, such that the ones expressed by Sunny this morning for these continued fractions on the behavior?
No, I never think about, even if we, about the even continued fraction, I don't know much about the statistical problem. One problem is that the continued fraction map of even continued fraction has infinite total mass invariant measure. So it has very different from the regular thing, but I don't know much about it.
Okay, thank you very much.
Yeah.
Thank you again.
Thank you.
Okay, so we start the final talk of the session with Samantha Fairchild, and the topic of our talk will be disjointness of flows and saddle connection on translation surfaces. Please.
Great. Thank you so much to the organizers for the invitation. This has been a really lovely conference. Thanks to all of you for showing up in the last talk of Thursday. I admire your perseverance. So what I'm going to do today is I'm going to talk about a project that is joint with Claire Burren. And then we had an appendix written by John Chaika. And I'm going to actually present this talk in the complete backwards order of the paper. So we're going to start with the appendix. And then at the very end, I'll be like, here's what we actually did in the paper. Okay, so first, we're going to define what is a translation surface. So translation surfaces has popped up a couple of times. The first definition is going to be a translation surface is a collection of polygons in the plane with sides identified by translations. Identified by translations with an equivalence relation up to what we call a cut and paste. Okay, so we're going to work with two examples for the entire talk and not work with any other examples. So the first example is going to be the torus. And so we're going to take the unit square. We're going to take 0, 1, I plus 1. And I'm going to identify the bottom to the top and the left to the right. And I'm going to get the torus. So this is hopefully well known to most people. Two things is our sides are identified by translations. So when I identify my sides, these are really complex translations. Z maps to Z plus I and Z maps to Z plus 1. Okay, and then I have to say, okay, what do we mean by up to cut and paste? So what do I mean by cut and paste is if, for example, I take the torus, whoa, okay. Whew. I'm going to take a different torus. And I'm going to take this torus and I'm going to slice this torus. So this is what we call by cutting. And that means I can cut my torus in a straight line. So then this is the cut operation. Doop. Up this and like this. So now we have side 1, 2. Now we have a new side 3. And then I can move anything by translations. So I'm actually going to move this guy over here, and I'm going to actually paste alongside 2. And then I'm going to get sides 3 and 1. But this is actually the exact same as my original torus. So I say that this torus, formed by 0, 1, I plus 1, I plus 2, up to a cut and paste is equivalent to my original torus. So I'm going to consider these surfaces. And one thing that we actually get from these surfaces is we can get a second definition. So this first definition is my favorite way to actually visualize translation surfaces. It's hard to work with mathematically because cut and paste is a very hard operation to work with. So the second definition is a translation surface is a pairing x omega, where x is going to be a Riemann surface, genus G, and omega is going to be a non-zero holomorphic one form. Okay, so what do I mean by Riemann surface? What I mean by a Riemann surface is that I have local charts into the complex plane. By placing this torus, I place this polygon in the complex plane, so I get actually very natural local charts to the complex plane. And so what happens on the case of the torus is I'm automatically getting a one form, which is DZ. So as soon as I write my polygons in the complex plane, I have a way to look at geodesics by looking at polygons at DZ. Okay, so so the case of the torus, it's a non-zero holomorphic one form, and it's actually a non-vanishing holomorphic one form, but things can get more interesting. And then that's why I'm going to introduce my second player of the day. Okay, so I'm going to take an L-shaped polygon. These are all parallel sides, despite the drawing. And I'm going to identify opposite sides of my polygon. Okay, so I have local charts for complex points, but something weird happens now at the vertices. Okay. So in the case of the torus, if I take this point, which is the left of 1, it's the left of 1 is the top of 2 is the right of 1. So this all maps, all of these vertices map to a single point. In the case of the L shape, we have actually the same thing. I take the left of 1, it's the top of 3, is the right of 1, it's the left of 2, it's the bottom of 3, it's the top of 4, is the right of 2, is the left of 1, and we're back to where we started. Okay, so this is nice. All of our vertices of our polygon map to a single point. But now if I pretend, and this was already mentioned in Sophie's talk, if I pretend that I'm an ant and I want to walk around and take a little tour around my vertex, if I take a tour around my torus vertex, I'm doing an angle 2 pi. So here our angle is 2 pi. But here, when we go around, we're actually going to have a total angle of 6 pi, which is an excess. So we can write this as 2 pi plus 2 times 2 pi. So this is a 0 of omega of order 2. So it's going to look like z maps to, sorry. So our one form omega is going to locally look like z squared dz around this point. Okay, so we have some things we need to keep track of, but this is all we need in order to define our first dynamical system. Does anyone have questions on the definition of a translation surface and the objects we're working with? Okay. Okay, so Dynamical Systems Conference, let's introduce our dynamical system. So the first dynamical system is going to be a flow. So we've seen a lot of discrete dynamical systems. We're going to actually be working with continuous dynamical systems here. So what notation did I use? F theta t. Okay. So given a translation surface, x omega, and a direction, theta, which is going to be in 0 to 2 pi, and a time, t, then I'm going to define the flow is going to be f theta t. So I'm going to go in direction theta. I'm going to start of x is going to be, I'm going to start at a point x. I'm going to flow with angle theta, and then I'm going to flow for time t. So we just flow time t at unit speed. Okay, so back to our example of the torus. I wanted to do this example just so that we have some connections to the previous talks. So hopefully most people have seen, and if not, happy to talk later. So on the torus, I want theta to be equal to pi alpha for alpha an irrational number. So when this is irrational, my flow on the torus is minimal. And one thing you can do is we can say, okay, I'm going to take this side of my torus, and I'm going to look at what happens as I reach this side. I'm going to define a discrete dynamical system, which we've been seeing a lot of. I'm going to define a discrete dynamical system of saying, okay, I reached this point. This is going to be my first point. And then I'm going to keep flowing. And then the next return time is going to be the second point. And so hopefully people will recognize this as the rotation by an irrational angle. And so one thing I just want to point out is, so if I go from like here to here, and I'm parallel to my saddle connection, then I can create kind of a box here. So I go from here to here in my flow. And then I can create another, keeping track of, okay, if I start on this side, so let's call this side B. If I start on this side and I start flowing, I'm going to end up reaching my interval over here. So what do we have? We have an interval exchange transformation on two intervals. So I take this AB interval and it maps to this BA. So this was mentioned before in a couple talks when we take interval exchange transformations. When you have the interval exchange transformation with two intervals, we get an irrational rotation. Okay, so that's the great. This is connected to what other people have done. Okay, so the facts that we've seen before, and I just want to write these down so we remember. This is uniquely ergodic. So this means that we only have one invariant measure, and that is the Lebesgue measure on the surface. We have something that is weakly mixing, but never strong mixing. Weakly mixing, yeah, in the case of the irrational, but never strong mixing. Okay, so this is the result on the torus. This is very classical. And now I want to say, okay, what happens in the case of the L and for general translation surfaces? So this is now going to be a theorem. So now I want to take for a translation surface. Oh, sorry. I don't want to do that. For Lebesgue, almost every theta, the flow F theta T has the following properties. So the first property is that it is uniquely ergodic for every translation surface. And this is due to Kirchhoff, Maser, and Smiley from 86. So it's uniquely ergodic. The fact that it's not strongly mixing actually goes back to the same result that Sasha used to cite for when IETs are not strongly mixing. So this actually results from the work of Katak. And then the fact that it's weak mixing for almost every translation surface. this is now suddenly much more recent. This was due to Avila and Forney in 2007. Okay, so even though this is really kind of the classical case on the torus, it actually took until 2007 till we got, weakly mixing, but it's only for almost every translation surface. I'm not actually going to talk a lot about what I mean for almost every translation surface. There is a natural class of translation surface that we can of measures that we can define on the space of translation surfaces. And the one thing I just want to say is a big theme of what we've been talking about this week is there's a lot of results that in ergodic theory are almost every. And we want to say, okay, from an almost everywhere statement, can we actually get an everywhere statement? So our goal, and what I want to highlight, is that we found a situation where we can go from almost every to every. And that's going to be what I want to advertise. Does anyone have questions? Okay. No questions? Okay. Okay. How many people know what joining of a dynamical system is? Disjointness? Okay, not everyone. Great, we're going to cover it. For everyone who knows what they are, you get to zone out for the next 3 minutes. They're all yours. Okay, so what we want to do is, so we talked about a single flow, but the thing is, on my translation surface, I have many flows. I pick an angle, and then I have lots of different flows. And we want to say, okay, if I flow in this direction and I flow in another direction, is there any relationship between these two flows? So that's the question we're getting at. So a joining of two dynamical systems, I want to do xt mu and y s nu is a measure on the product space such that a measure rho on the product space. And what do I want? Well, I want rho to be invariant under T cross S. And the other thing I want is I want my measure to project down onto the measure on X. And similarly, I want the measure to project down onto the measure on Y. So what we're doing is, I said we want to, understand how do things interact. And so adjoining says, okay, if I have two dynamical systems, so in our case, X and Y are going to be the same Riemann surface. T is going to be a flow in one direction. S is going to be a flow in the other direction. And we want to say, okay, what do we know about the two of them when I want to look at, how do they actually interact with each other on the product space? And we say, X T mu and Y S nu are disjoint if mu cross nu is the only joining. So what does this mean by disjointness? It says, okay, if mu cross nu is the only joining, this is really kind of a unique ergodicity type statement on the product space. So in particular, note, disjoint implies not isomorphic. So this is actually a stronger statement, but this is an exercise, for example, in Einsiedler-Ward's book saying any two disjoint flows are not isomorphic. So yeah, it's always a good question to say, if I take my dynamical system and you take your dynamical system, can we tell if you have the same dynamical system? Are they isomorphic? And disjointness is a way of saying, no, they really aren't. And they're so not isomorphic that really we have a unique ergodicity statement. Okay, so now we have a theorem which is due to Teichmüller and Hubert. And this is from 2017. And they said, okay, for almost every translation surface, and for almost every pairing theta psi in 0 to pi squared, the flows f theta t and f psi t are disjoint. Okay, so one thing that I want to point out is we say something is for almost every theta m psi. So if we look at the example of the torus, well, whenever we have periodic elements, we really need minimality. Like we really, because we have an invariant measure on each kind of period, that we don't want to allow those. So to strengthen almost every theta m psi is not going to happen. We can't do it because we can't even do it on the torus, which is like the easiest case. So what we can hope for is to say, okay, we want to do it for almost every theta m psi and show that we have disjoint directions, but we want to actually, can we say this for every translation surface or for every translation surface in a family instead of almost every, because then that allows us to really get our hands on it. Just like in the case of the torus, you take the square torus, we can get our hands on it and we know this fact. Okay. As a corollary, and this is something I did not know actually from this result, but as a fun fact, the techniques apply to branched covers of tori. So for the experts in the room, what does this mean? This works for every square tile translation surface. So in particular, whenever we have arithmetic Veitch surfaces, we can actually see that they're disjoint for every Veitch surface, every arithmetic Veitch surface. So really the difficulty was saying what happens for non-arithmetic. For the non-experts, that's a nice corollary. And we're just going to talk about saying, you know, how do we go from almost every to every? Okay, so I'm ready for my theorem statement. Great. So the theorem, which this is with Burin, myself, and Teichmüller, and this is part of the appendix, which has been, it'll show up maybe this year, you never know. So it's been accepted, but hasn't appeared yet. So what we can say is for every Veitch surface, for almost every theta m psi, the flows f theta t and f psi t are disjoint. Okay, so we can actually say something for every single Veitch surface, which means I should tell you what a Veitch surface is. So in order to define a Veitch surface, I now want to define my second dynamical system of the day. So the second dynamical system, I mentioned we can really look at the space of translation surfaces. So second dynamical system is going to be an action of SL2R. So for my action of SL2R, I say, well, SL2R will act on a translation surface X omega. And what is it going to do? It's going to act linearly on the polygons. So our polygons live in C. We can act like a linear map in the plane. in particular, notice that because we have parallel sides, the SL2R is going to preserve parallel sides. So it's not going to mess up our identifications by translations. So if we take, for example, 1x, 0, 1, and we apply this to the square torus from above, so we apply it to 0, 1, I plus 1, then this is going to give us some surface which is skewed 0, 1, I plus x, and then I plus 1 plus x, for x in the real numbers. So if you remember from our previous example, if x is equal to 1, we have that 1, 1, 0, 1 applied to the torus is equivalent by cut and paste to the torus itself. So what does this mean? It means we have an action on the SL2R, and we have an element 1, 1, 0, 1, which is in the stabilizer. So we're going to define SL of x omega is going to be the stabilizer. So it's going to be the set of all G in SL2R such that G x omega is equal to x omega. Okay, and a surface is called a Veitch surface. If SL of x omega is a non-uniform lattice. So what do I need for a non-uniform lattice? Well, I need a discrete subgroup and I want to have the volume of SL2R mod SL of x omega is finite. This is exactly what makes it a lattice, is a discrete subgroup which has finite covolume. But it's going to be non-uniform in the sense that SL2R mod SL of x omega is not compact. Okay, so what is our theorem statement? Our theorem says for every Veitch surface, so that means every surface which has this large stabilizer group, so this means that they have a lot of symmetries, and so for every Veitch surface, in almost every direction, the flows are disjoint. So the torus is a Veitch surface. I think we've already seen this before, but we have SL of the torus is equal to SL2Z because SL2Z is generated by 1101, which we know is in the stabilizer group, and exercise is also stabilized by 0, -1, 1, 0. So that's the stabilizer group of the torus. And then for the stabilizer group of my L shape, I can't get this of each surface for every L shape, but what I can do is I can say, okay, I want this side length to be the golden ratio, which is 1 plus the square root of 5 over 2. This side length is also going to be the golden ratio. This side length is 1, and this side length is 1. So under this, then we have the stabilizer group of the L shape is exactly 1 golden ratio 1 and 0 minus 1, 1, 0. So this should hopefully look familiar to some people who were at the poster session, because Laura was talking about Hecke triangle groups, and the L is an example of a surface which has the 2, 5 infinity Hecke triangle group as the stabilizer. Okay, so this is the statement of the theorem and the objects. Does anyone have questions? So if I take an L shape, what I really have with my L shape is I have 4 vectors, which are complex vectors. Yeah, so I really have, like, for example, I can take like these 4 vectors, v1, v2, v3, and v4. And so this is a kind of a generalized L shape. And what can we say about these vectors? Well, we could a priori move these vectors in the complex plane and still have an L shape if we do small perturbations. So this gives us, one way of perturbing it. In general, the stabilizer group is trivial. So for kind of almost every choice of my vectors, this stabilizer group is going to be trivial. And then if I have, you can have non-trivial stabilizer groups that aren't this nice. So Veitch surfaces are the ones where, because you can have, yeah. So in general, you want to think of these are really like a measure 0 condition, which gives us in the full space where we have the high symmetries. So there's many examples, but they are very small in the sense of if we look at our parameter options for our side length choices.
Or how does it relate to unique ergodicity?
Oh, so the idea of how does adjoining relate to unique ergodicity is, okay, so you have your space of invariant measures. So I have my space of invariant measures. The ergodic measures are the extreme points. And then I am uniquely ergodic if there's only one measure in there. And so what is disjointness? Disjointness is saying, okay, I have 2 different dynamical systems. They each have their own space of invariant measures, but I want to look at the invariant measures that's on both of them. And so you can have a large space of invariant measures on the product space. And then this is saying there's actually only 1 point of all of this in the whole space of invariant measures. Yeah. The 2-5 infinity triangle group is SL of L, is the stabilizer of L. So the 2-5 infinity triangle group is generated. Where is the large white chalk? Okay. Is generated. So SL of L is equal to the 2-5 infinity triangle group. And it's defined to be, so in general, you take 0, -1, 1, 0, and then your other generator is always 1, 0, 2 cosine of pi over q, 1. And that's the 2q infinity triangle group. And what is this exactly? It's the, if I take the hyperbolic triangle of angle pi over 2, and this angle is pi over q, and then I have infinity as my other triangle, and then I flip it once, and then it's all of the orientation. So it's all of the orientation preserving automorphisms of this triangle. Any others? Okay, so now I want to tell you, what's over there? Okay, so now I want to tell you how would we actually have a hope of proving this. And for anyone who wants to look at our paper, disclaimer, it's not actually super easy to show we have disjoint. So I'm going to give you a quick idea, and then we can always talk through more ideas later. So the idea is So in order to prove disjointness, we're going to add another definition. So we have a sequence, Tj, for j and n. So we're going to be taking our flow as in T for any real number, and we want to take subsequences so that we're going to reduce this to discrete sequences. Is a C, sorry, I don't want to add that, is a partial rigidity sequence if there exists a constant greater than 0 and a set AJ with the mu of AJ bigger than C, such that the limit as j goes to infinity of the average of the distance over AJ, the distance of the flow between points in AJ dx is equal to 0, d mu. Okay, so what is this saying? It's saying, okay, so I need small sets. They can be quite small, but they have to be bounded below. And I want to take small sets where when I flow with my flow, I'm not actually getting very far away. I'm kind of always coming back really, really close to myself on average. So that's a partial rigidity sequence. And it's a mixing sequence if for all f and g in L2 of mu, we have that the limit as j goes to infinity of the inner product of the composition with the flow is equal to the integral of f, the integral of g. Okay, so intuitively, mixing says that, okay, so if I think of f as like characteristic function of a ball, of a set A, and G is characteristic function of a set B. Mixing says that if I move with flows, I'm kind of moving everywhere, that things are really independent. And rigidity is rigid and saying, you know, you're not actually going that far away. And these two facts are actually enough to show disjointness. So I wanted to share this because I actually think it's nice to know when things are disjoint. And I didn't know about this before. So if there exists a mixing sequence, which is, a mixing sequence for f theta, which is a rigidity sequence for f psi, then f theta and f psi are disjoint. Okay, so as a remark, by Avila and Delacroix from 2016, they said that f theta t is weak mixing for every non-arithmetic Veitch surface. So if you don't know what a non-arithmetic Veitch surface is, all you need to know is that in the case of this L shape, we're weak mixing. So once we have something that's weak mixing, so remember weak mixing says on average you're mixing. So if you're weak mixing, on average you're mixing means that you can find mixing sequences. But if you have a sequence which you can find a mixing sequence, which is also a rigidity sequence for the other direction, then these are going to be, this is a sufficient criterion for disjointness of flows. Okay, so in my last 10 minutes, I'm going to state a sufficient condition, which is then going to hide the hard part of this. Okay, so a saddle connection is a geodesic gamma, which is connecting corners, vertices. And the holonomy vector is going to be the integral against gamma of omega, which just lives in the complex plane. And S is going to be the set of holonomy vectors. Alveolar Delacroix is for every non-arithmetic. Oh, yeah. So for, oh, yeah, you're right. I did not, for every non-arithmetic beach surf, for every non, yeah, exactly. I would have to look back in the, I don't know if it's for every non-periodic. I don't remember. I would have, yeah, I have to double check. Yeah, that's something that's worth double checking. Okay. Okay, so holonomy vector here is a geodesic, which starts and ends at a vertex in my torus. And V gamma, well, I'm integrating against dz, so I just get the horizontal and vertical displacement. So in general, I'm going to put this over here, I guess. Okay, so in general, the set of holonomy vectors of the torus is equal to the primitive integer lattice. So it's the set of all A, B in Z2 such that the GCD of A and B is 1. And SL is given by SL. Oh, wow, this is terrible notation. I regret this. SL applied to E1 union the stabilizer applied to 1 over the golden ratio, E1. So what happens on the L is, on the L shape, I have geodesics come in parallel pairs. I can do this geodesic, or I can do this one, and these are parallel. So this is gamma 1, this is gamma 2, and they're parallel but scaled by 1 over the golden ratio. Okay, so set of holonomy vectors, great. So I'm going to end with a criterion that then tells you what that paper was actually about. So it suffices to show for all epsilon greater than 0, there exists an eta bigger than 0 such that the lim sup as r goes to infinity of the number of x in the set of saddle connections intersect the ball of radius r centered at the origin such that the number of s intersect the ball of radius eta centered at x has at least 2 points divided by the number of points in the ball of radius r is less than epsilon. Okay, so what is this saying? I have x is in the ball of radius r, and I want to look at the neighborhood around x of size eta, and I'm saying I have at least 2 points in here. So if we look, for example, at the integer lattice, let's say this is x, and I want to look at a ball of radius, 1/8 around x. On the integer lattice, I'm never going to have 2 points. I'm never going to have a second point in here. So there's never a point in here. Why? And these are called eta friends. So here, this isn't going to happen, and it doesn't happen because we're uniformly discrete in the case of integers. In the case where we're non-arithmetic, we are not, the set S is not uniformly discrete. So what does it mean? When you're discrete, it means for every, I can pick a radius where, for example, 1/8, and I can place a ball of radius 1/8 around every point in my set, and I don't intersect any other points in my set. Not uniformly discrete says I'm discrete, but as I go out to infinity, I can find points which are arbitrarily close together. So what does this say? This is a quantitative non-uniform discreteness. It's saying, okay, I want to take the number of x in the ball of radius r, which have a point within eta of it. Think of eta as very small. And I'm going to normalize based off of the number of points. And this is less than epsilon. So this says that there's at most an epsilon proportion of eta friends in S. Okay, so in the last minute or two of my talk, I want to tell you how this happened. So I was talking to John Chaika mid-pandemic. We were like, what are you working on? And I was like, I don't know, what are you working on? And we were like, okay, you know, maybe let's talk some math to inspire ourselves. And so John introduced this concept to me of eta friends. And he said, okay, I have a problem for you. I want to find out, you know, can I control for a translation surface the proportion of eta friends that occur in my set of saddle connections? And I said, oh, you know, for beach surfaces, I know how to do this based off of my work with Claire. And so this was a really nice thing where he just stated an open problem. And I was like, cool, I know how to do that. And so this is how we actually came across this collaboration. And he was the one who did all of this work of, you know, translating this idea of saying, okay, what does it mean to be disjoint? It means you need rigidity sequences and mixing sequences. And this is really going to allow us to get our hands on, you know, when things end up close together. And so this is actually the criterion that he needed. And so the techniques that we use is, it's called the Siegel-Veitch formula. We end up using a lot of like arithmetic number theory results. We need to understand, you know, what is the spectrum of the Laplacian for H mod gamma, where gamma is a non-arithmetic lattice. So all of these tools came into play. So if you look at the paper, it's a number theory paper with a dynamics appendix. Okay, that's all I had to share.
Are there any further questions for the speaker? No? Yeah.
So you wouldn't be able to generalize this to anything other than a beach surface, right?
So the techniques that we used in this paper is very specific to the beach surfaces, because we really use, so for any beach surface, the set of holonomy vectors is actually a finite union of orbits of the stabilizer group. So we really use those techniques. There are other techniques. I have a paper with John Chaika actually, and a paper with Jayda Bethray and Howie Mazer, where we do try to understand how pairs interact for generic surfaces. But we are not at the point where we can do this. We can only look at pairs, you know, we can look at their angles. We can look at, like Luca Marchese has work where you look at the relationship between angles and distances in pairs. But this really capturing, you know, the whole ball of radius epsilon around another point, this is not an SL2R invariant set. And so it actually is very hard to get your hands on it. So we did think about it. The techniques we have right now really depend on the ergodic theory of the SL2R action. And then we don't really have, it is work that needs to be done. Yeah.
Thank you.
Yeah, maybe this is more a question for John, but if maybe you also have, so this disjointness for almost every, so you proved it for which, it's for almost every. Do you know if there's an expectation there for other lossy should be true, or could there be counterexamples? Could there be exceptional translation surfaces where it fails?
Yeah. So when I talked to John about this, John had told me like his conjecture was that it was true for every surface, because we know it's like, do I still have it up? Yeah. So, okay. So it's not here, but I mean, they have this result for almost every surface. And I think that okay, what do I want to say? What I want to say is, I think it's one of these things that, you would hope it's for every surface. I think John was willing, before we did this, John said, yes, I do think that it is every beach surface. I think he was relatively confident about that. I think the problem that happens is you actually have, like, in a general surface, if you want to do it from like a square tiled version, you have an accumulation of cusps. And so when you look at your set of saddle connections, the risk is that you might have a higher proportion of epsilon friends. And so we think there could be a higher proportion of epsilon friends, but this having, not being able to get this result doesn't mean that we can't get disjointness. So this is, a sufficient condition that, like, this is something that I would like to be able to show based off of our estimates, the way everything's been working so far, this should work. But yeah, we don't actually know. So I would guess they probably wouldn't be so bold to do a full conjecture for every surface.